y 2. Prueba de audio. Prueba 1, 2. Y 2.
Deberían estarle llegando.
Hello. Good morning, everyone. Welcome to day 3. I hope you're enjoying the meeting. It's my pleasure to introduce the first speaker of the session, Kevin Murphy. Kevin was born in Ireland, but grew up in England. He got his BA from University Cambridge, and his Master in Engineering from U Pennsylvania, and his PhD from UC Berkeley. He then did a postdoc at MIT and was an Associate Professor of Computer Science and Statistics at the University of British Columbia in Vancouver, Canada, from 2004 to 2012. After getting tenure, he went to Google in California on his sabbatical and then ended up staying. And he currently manages a team of 28 researchers and engineers at Google DeepMind. The team works on generative models, including diffusion and LLMs, reinforcement learning, robotics, Bayesian inference, and various other topics. Kevin has published over 140 papers in refereed conferences and journals, as well as 3 textbooks that many of you probably know, on machine learning, published in 2012, 2022, and 2023 by MIT Press. The 2012 book was awarded the D. Groth Prize for Best Book in the fields of statistical science. So thank you very much for being here.
Good morning, everyone. Thanks for the invite. It's a pleasure to be here. I have been to Santiago before, but it was like 10 years ago, and so it's nice to come back again. Okay, so I'm going to talk about, this is a very long title. So the first thing I'm going to do is explain what all the words in the title mean, because it's a sort of this is like half tutorial and half research talk. But I wanted to first give a bit of background about why I chose to talk about this topic. So there's actually several reasons. So first, it's just like pragmatic. This is all published work. I'm not giving away any Google secrets. In fact, the majority of this work was done with external colleagues, primarily with Gerardo Duran Martin, who's from Merida in Mexico, but he's a student in the UK that I've been supervising. So that's the first reason. Second reason is I just find this material super beautiful. It's like very elegant mathematics. And it's not about like brute force scaling. You don't need big, TPU clusters. You need clever ideas. And so these ideas, most of them are not very new, but like we're sort of revitalizing them. So I think there's a lot of potential for this to become mainstream in the deep learning era. And then the third reason is, it's like Gerardo's from Mexico, so I thought, okay, there's a little connection to KHIPU. So that's the why. So what about the what? So I'll talk a little bit about what is sequential decision making. I don't know the background of y'all, but I'm assuming it's pretty broad. Hopefully you've seen many of these things. Then I'll talk about online Bayesian inference, which is the tool that we need to do sequential decision making under uncertainty. And then I'll talk about Variational Bayes, which is the tool we use to make it computationally efficient. And that's sort of background stuff. And then I'll dive into some of the algorithmic developments that we've been developing over the last 2-3 years, using Variational Bayes and trying to make it more scalable using tricks essentially from linear algebra, low-rank matrix decomposition tricks. And then I'll talk about a couple of applications of all of this stuff. So I'll talk about contextual bandits, which is a very widely used tool that it will be good for you to learn about if you don't know, and Bayesian optimization that's closely related. And then if there's time, I should watch the clock. When do you want me to finish? 10:20? Okay, perfect. If there's time, I'll talk about an extension of this work where we go beyond like classical Bayesian inference and consider like semi-Bayesian approaches, generalized Bayesian approaches that are more robust. So that's the menu. Should I take questions during the talk? I'm happy to take questions during the talk. So just interrupt any moment. In fact, I'll pause right now. No, okay, all right. Not much to ask about. Okay, so this is the big picture. This is what I'm going to talk about today. So the setting is there's a bunch of data streaming in. So imagine you're an agent, you're in the world, and there's like data coming at you, and you've got to do something, right? So you get some state vector, which is a representation of the world that you see, and you have to perform an action. And after every action, you get some feedback from the environment, which we call a reward signal. And so you've got this past stream of data that you've collected yourself, and then the new state arrives, and you have to make a decision, what should I do? So your decision is a hat. This is the action that you take, and the function that tells you what you should do is called a policy, and that's denoted by pi. So that's a function of the current state and everything you've seen so far. And the goal is basically to learn this policy function pi so that you maximize the sum of the rewards that you obtain at each step. Okay? So that's the, and we can call these reward functions utility functions because we're in the School of Economics right here, and this is called the maximum expected utility principle. So this is the foundational of rational decision theory, right? It goes back to von Neumann and Morgenstern, I think. So it's very, very old. In machine learning, for some reason, we like to minimize losses instead of maximizing rewards, but they're mathematically equivalent. Okay, so the whole talk is going to be about how do we compute this policy and update it incrementally as the data comes in. So just to give a concrete example of a sequential decision-making problem, think about supervised learning. So the state is a feature vector x, and the action that you take is the label that you predict y. And you've got a previous set of inputs and outputs, and now a new input arrives xt, and you have to predict what the label is. That's yt. So your action here is one of k possible labels. And the loss function or the reward function, it depends on how close your prediction is to the truth, right? So that could be 0, 1 error. I'll talk about that in a second. So, so if it's a classification problem, you might use 0, 1 error. So if these two things are equal, you get 0 loss. If they're unequal, you get a loss of 1. Okay? So I'm sure you've seen this. But we could also do regression in the same notation will work for, say, a regression problem where this might be squared error. So it's the squared difference between the two quantities. So let's look at regression for a second. So hopefully you've all seen this. This is like page 1 of my textbook, basically. If you're trying to minimize, what's the best thing you should do, right? If you want to minimize your expected loss. Well, you just write down what the quantity of interest is. It's the expected loss as a function of the action that you can take. So you plug in definition of expectation, definition of loss, do a little bit of calculus, and then you find it's the posterior mean. So that just says you should predict the expected value of the output conditional on what you've seen. And that's the best thing you can do. So that's the optimal estimator for L2 loss. Okay, so that's well known. And then similarly for classification, let's consider you could have this confusion matrix, right, where you've got the truth on the rows and the actions on the columns. And if the truth matches, if you predict the right label, you get 0 loss. If you predict a label of 1 when the truth is 0, you get a false positive loss. And then vice versa for the false negative loss. So if we assume these false negatives and false positives cost the same, let's say a unit of $1 or 1 unit of whatever, then we can derive the optimal estimator. So you just crank through the math and you find, lo and behold, it's the most probable label, the map estimate. Okay, so this is hopefully very familiar to all. Okay, so what we want to do is we want to do this kind of, say, classification problem or other decision problems. We want to do it online as the data streams in. That's the focus of the talk. So this is a concrete example. I'm sure you've seen this is the 2 moons data set, and probably you're used to the setting where you've got like a whole batch of data and you fit, say, a neural network to it. But what we want to do is learn this network online as the data streaming in. And it could be potentially from a non-stationary distribution. So this is just some eye candy of our method in action. I'll explain the method later. After 100 data points, you haven't seen a lot of data. The model's not very good. 200 data points, it's learning this line. And as you get more data, the complexity of the model increases, the effective complexity. Okay, so how are we going to achieve that goal? So what we're going to do is we're going to represent the unknown parameters of the data distribution, which in this case is the classification function, by theta. And these parameters could potentially change over time, or maybe they're static constants, but they're unknown. So these are like the hidden variables in our graphical model. And then at each step, what we observe is the output label that depends, of course, on the hidden parameters, so nature's distribution, and then the inputs that we also observe. So the goal basically is to estimate the hidden parameters as a function of the data. So this is a special case of what's known as belief state filtering in the engineering literature. So this is a probabilistic graphical model, and what we're going to try to do is to recursively estimate the belief state, which is the probability distribution over the unknowns given the data, and that represents our beliefs about the underlying function that we're trying to learn. And when we have that, there are 2 things we can do. So a new piece of data arrives, we can predict what the output will be, So that's like a classic prediction problem in machine learning. And then after we observe the output, so this is before we see y, so we predict, and then we see the output, and then we update our beliefs with the new piece of data, and now we say, it looks like the function goes up to the right, or whatever. Okay? So this is making a connection between state space filtering, which all the engineering people in the room will know about, and machine learning, right? So, okay, so now we're going to dive into how we do these computations. So this is classical stuff. This is just super beautiful, I think, the predict update cycle. So what we have is we're trying to predict what the parameters will be at the next step. So we start with our prior belief state, which is the input to the process, and we have a dynamics model, which is how the parameters change over time. And that could be like they don't change. It could be constant, or it could be, say, a Gaussian random walk. I'll talk about that later. And then so we basically take a distribution, we push it through our dynamics, we marginalize out the past, so we get the one step ahead predictive distribution in parameter space. And then an input comes along, and we can project that distribution into observation space to make a prediction about the output given the past, right? So that's the predictive distribution in data space. And then we can use that to make decisions. We take an action, and then nature comes back and says, this is the true label or the true reward. So you update your beliefs with the new piece of data. So that's just Bayes' rule, right? It's the likelihood times the prior normalized. So that's the update step. So the whole talk is how to make these equations run fast, basically. So this is called turning the Bayesian crank, right? This is the beautiful thing about Bayes, right? It's pretty easy to write down the problem, and then it becomes a computer science problem, effectively. There are some modeling issues as well we'll talk about, but that's not really the focus. So on the modeling front, we're going to make some assumptions to make the computations tractable. So we'll assume that the parameters evolve over time according to some Gaussian process. So F is the dynamics of how they drift. Maybe it's the constant function. And then Q is a little bit of noise that we add to let the parameters wiggle around. And then H is the observation model. So this could be, say, a neural network that generates outputs given inputs. And it depends on the unknown parameters theta. Okay? And we might add some observation noise if it's a regression problem, or it could be a classification problem or something else. So this is called a Gaussian state space model. Not to be, well, okay, there are other kinds of state space models that are used in the deep learning literature, but they're not probabilistic. Let me give some examples of these functions. So we'll start with the observation model, which is really the main thing of interest. So if it's a linear model, this is called a linear Gaussian system, and then all the math is beautiful, and I'll give examples of that shortly. But we generally want to consider nonlinear models. If it's a regression problem, then it's natural to put a Gaussian distribution on the output. If it's a classification problem, we might use a Bernoulli distribution or a categorical distribution. And this function H could be, say, a little MLP, a multi-layer perceptron. We don't really care for this talk. It's some differentiable black box function. Okay, so that's the observation model. So that's whatever neural net, like this could be a transformer, whatever. All of deep learning goes into the H function. I'm not going to talk about that today. It's just a black box function. Okay, so then you can dive into details and talk about skip connections and all of those kinds of things, which I'm sure other people have covered. But for us, it's just a nonlinear function that's differentiable. Okay, the dynamics, a common assumption, like I said earlier, is that the parameters evolve according to a Gaussian random walk. And depending on this dynamics matrix and this noise matrix, we can recover various special cases. We'll mostly consider the static case when the parameters not changing over time, and that's like not adding any noise, right? It's not drifting. It's unknown, but it's always the same, and you're just accumulating data. But one nice thing about this framework is that it can handle drifting parameters and non-stationarity just organically. So it's very good for that setting. Alrighty. Okay, so there are two modeling assumptions. We have a likelihood function and we have a dynamical prior. Okay, so now the rest is Bayesian computation. So since we're assuming, we're going to, the other approximation is a very strong assumption, is that the posterior belief state will always be assumed to be Gaussian in this talk. Okay, so we can represent it by a mean in a covariance matrix. And so the mean is just like your point estimate of the state, and the covariance matrix is some representation of your uncertainty. And obviously this is unimodal, so it's very restrictive, but it's very fast. And so it's a trade-off. And this can be used as a subroutine inside of more complex approximations like mixture models or particle approximations. But today it's all Gaussians. One of my colleagues says, oh, this talk, all I'm doing is like pushing Gaussians around. Yes, it's true. But you know, it's kind of fun to do that. So, I mean, it's better than just pushing point estimates around. It's like the next level beyond that. So to do the predict step in parameter space, we have our previous belief state, which is a Gaussian, and we push it through this linear Gaussian system, and then the output is just another Gaussian, right, with updated parameters. So the notation is t given t minus 1 is, I predict t given t minus 1, given the past, right? So this is standard notation from the engineering literature. Okay, so that's a closed form analytic thing, very simple. And then that's predicting in parameter space. We push our parameters through one step. Now I want to predict what I think I'll see, conditional on some inputs. So I have to solve this integral. So the most common thing that people do is they just do a Monte Carlo approximation. So you sample from your posterior k parameters, and then you just plug them into your likelihood function, and then you just predict. You get a bunch of samples, and then you can average them. But if your model is linear Gaussian, you can push the Gaussian through the linear model analytically, and then derive the predictive distribution in closed form. So that's a handy trick that avoids Monte Carlo. Okay, so that's, you see, we can make predictions. So if I have a belief state, I can make predictions, and if I can make predictions, I can make optimal decisions. And I'll come back to the decision-making stuff later. Right now, I'm just talking about the belief state aspect. Okay, and then we observe some new data after making our decision. Nature says, okay, this is the actual truth. You made a prediction, but this is how it really is. So you update your belief with a prior. Sorry, your prior is this one step ahead predictive distribution, and then your likelihood is the thing we discussed before. And then we want to multiply prior and likelihood, normalize, compute the posterior, and that's where the computational fun and games begins. Okay, so let me take a break. Any questions before I continue? All right, hopefully crystal clear. So as a special case, let's consider the dynamics is linear, like I said, and the observation model is linear. Oh, yes. Yeah. I'll talk about that later. Okay. Yeah, good question. Yeah. So this is all a slow build-up. Okay, so going back to just this setting. So right now, I'm not even talking about decision-making yet alone, RL. I'm just talking about inference in this graphical model. Okay. So if this link here is linear Gaussian and the dynamics is linear Gaussian, then you can compute the predict and the update step in closed form, and this is called the Kalman filter, and it's all very beautiful. And the derivation's in my book and many other places, so I'm not going to go through it now. But it has this, maybe it's worth dwelling on briefly. It's actually fairly intuitive, right? So the predictive distribution, the variance is basically your prior variance, and then you add some extra noise to it. And then your mean is just you take the prior mean, you push it through your linear function. So your observation takes what you think the parameters are and just pushes it through your linear observation model, right? So that's your prediction of what you think you'll see. And then when you actually make an observation, your new belief is your old belief plus a residual term, the actual minus prediction, weighted by this matrix K that's called the Kalman gain matrix. And that's a ratio of the uncertainty that you had in your prior relative to the uncertainty you have about your observations. So if your observations are very informative, then you pay a lot of attention to the data. If they're very noisy, then you pay more attention to your prior. So you can do all this in the scalar case, and then it all becomes very intuitive. Okay, so concretely, like Kalman filtering was originally developed for tracking problems, I believe. So imagine like there's a little airplane, or maybe it's a missile or something, a drone flying along through the sky in 2D in this case, and we're trying to estimate its location and velocity. And what we observe are these green circles, which is like a point estimate, like a ping of a radar that tells me where it is. And we're going to assume that the model, the unknown state is the location and velocity, so it's a 4-dimensional vector, and it's going to evolve according to Newton's laws, right? So new location is old location plus delta times velocity, and then the velocity is the new velocity is the old velocity plus a noise term representing random perturbations from the environment. And then the observation function just extracts the first two components, right? It just projects out the location components of the vector, and the velocity is hidden. But you can infer the velocity just by, computing the difference between two neighboring locations, right? So the belief state is represented by these circles. This is a Gaussian 2D projection of the belief state about where you think the object is. And you can see there's a mean, which is shown by the red line, and then there's some notion of uncertainty. Okay, so that's a visualization of what we're doing, right, in a simple setting. And here's a little movie that Gerardo made. So the data's streaming in, and then the gray line is an online estimate of the posterior mean. Okay. So that's like an application to some sort of engineering problem where we're tracking moving objects. It has all kinds of applications in biology, and people in econometrics use this all the time. So you can also use it for fitting statistical models, like machine learning stuff. So imagine, like I was explaining earlier, that now the unknown state of nature are the parameters of our model, and suppose it's a linear regression model. Okay, so the output is just a linear function of the input, and the weights, the theta, are the weights of your network, as it were, and we want to estimate those parameters as the data streams in. So here's a plot where the true parameters are in the dotted line, and then the wiggly lines are our posterior mean estimates, and as more data streams in, the error reduces to the offline estimate, the batch estimate. So that just shows you how, like, exactly the same machinery. So this is exactly equivalent to, after you've seen all the data, you just do one pass through the data. This is Bayesian linear regression. And the posterior mean is equivalent to ridge regression, right, the map estimate. Okay, so hopefully that's all familiar. Okay, so now that's all like very beautiful closed form stuff. But now we don't really want to use linear models, right? We're in the deep learning era. We want to use nonlinear models. That's what deep learning is, where H is like some billion parameter or trillion parameter network. So we want to learn the parameters of this nonlinear function as the data streams in. So here's a slightly more complex example where it's still 1D, but the underlying functional form as a function of time is clearly nonlinear. And so we can just approximate it with like a 2-layer neural network. And we're going to estimate the parameters of the neural network one data point at a time. And that's shown in the bottom plot. So the key question is, how do we do that? So a classical technique is you can take your nonlinear model and you can just linearize it at every step. And this is called the extended Kalman filter. So you take your dynamic, you have your mean at the previous estimate, and then you compute the Jacobian of your nonlinear function. So that gives you a linear matrix, and now you apply the Kalman filter, and you just do that repeatedly. So this is a classical technique, and you can do that. So EKF for training neural networks is like 30 years old. Nando De Freitas, who's in the audience, has worked on this. Many people have worked on this. You can think of it as like a second-order optimization algorithm, where the covariance matrix is your preconditioning matrix. And I'll make that more clear shortly. Okay, so this is classical. But it's still restricted to the land of Gaussians, and there's sort of no control over the quality of the approximation. So we'd like a more general solution to this. So that's where variational Bayes comes in, and this will be the end of the tutorial section. So the exact posterior is the prior times the likelihood. So we can try to approximate that with some function, so some distribution Q. And what we're going to do is we're going to pick Q from some family that is computationally tractable, such as Gaussian. The true posterior might be non-Gaussian. We're going to approximate it with a Gaussian. So we need to optimize the parameters of our Gaussian approximation. So that will be psi. These are the variational parameters. So we're going to pick a distribution that's as close as possible to the truth, measured using KL divergence. So that's what variational inference is all about. So it converts Bayesian inference into an optimization problem, which is a very good move to do because we have lots of tools for optimizing things. So if we just crank the math on what this KL is, you can expand the various terms, and at the end of the day, it decomposes into an expected log likelihood and a KL penalty term between the posterior and the prior, which acts like a regularizer. So hopefully you've all seen this before. This is the evidence lower bound, the elbow. that everyone uses when they're training VAEs and so on. So here we're using the same math, but for Bayesian parameter estimation. Okay, so pictorially what's going on is there's some true distribution over the unknowns. Here the Z or Z, and in my talk the theta. This is a picture from Dave Bly, so he used Z. So this is the true posterior. This circle is like the set of things that you can actually represent, let's say with a Gaussian, and you want to find the point that's the closest in KL divergence to the truth. So you just take the truth and you project it into your set, and you're trying to find that point. And you just do some iterative optimization problem of that objective. Okay? So if we want to do that online, it's basically the same setup, but we're going to have a negative elbow. So let me define all these words. So the elbow is this quantity, which is called evidence lower bound because it's a lower bound on the log marginal likelihood, which is also called the evidence. And the negation of that is this expression, which is the negative elbow. So we're going to try to minimize this negative elbow at each step, right? So we get a new distribution at every step. So it's the same as standard variational Bayes, but we're doing it online. And the key point now is that our regularizer, instead of to a fixed prior, is to our previous posterior. So that's sort of the main change. All right. So that's the setup. That was 25 minutes of background, but I think it's important, especially since this is a summer school. Okay, so with that as background, now I can talk about some of the new work we did in the space over a few years, and this is with various colleagues. And basically, we're trying to make that stuff that I just described go fast, is the name of the game. So let's start by talking about this optimization problem. So we have the elbow loss function, and it's parameterized with the variational parameter psi, which are like the mean and the variance of this Gaussian. So we can use something called natural gradient descent, which is just like regular gradient descent, except you multiply it by the Fisher information matrix as a preconditioner. So that will like change the geometry of the space so that it will converge more quickly. So it exploits the fact that we're working in a non-Euclidean space. And there's a fact that follows for exponential families that I'm not going to have time to go into, that the natural gradient, which is the Fisher information times the gradient, is equal to the vanilla gradient with respect to the moment parameters. So there's some technical stuff I'm not going to be able to explain today specific to exponential families, of which Gaussians are an example, right? Where you can convert between dual and moment parameters. So there's some fancy math here going on under the hood, but basically it means you can exploit properties of these probability distributions to make the optimization go fast. So this elbow, remember, is the expected order likelihood times this plus this penalty term. So concretely, the moment parameters of a Gaussian are the mean and the variance that you know and love, and then the natural parameters are the precision matrix, sigma inverse, and then the precision weighted mean, sigma inverse times mu. And you can convert from one to the other. Obviously, you can see you can convert from one to the other. So that's a general property. So that's just a fact, and we can exploit that to make our gradient optimization go fast. Yes, exactly. The gain is avoiding the computation of the inverse. Okay, so applying this technique has been called the Bayesian learning rule. There's a paper by Matias and Harvard Rue. Matias is a former student of mine. He's a professor at Tokyo now. And so they have this nice review paper that if you're interested in this, you should go read, because he makes the connection between all of this and other forms of optimization used in ML, like Adam and Vaughan and all of that. Okay, so what we wanted to do is apply that kind of machinery in this online setting. So if you write down the Bayesian learning rule in the online setting, it's the same as before, but we have these T subscripts everywhere. So we're trying to minimize or maximize the expected log likelihood with this penalty term that's the new posterior relative to the previous posterior at the previous step, okay? So now, if you look at that optimization, it's going to be an iterative optimization. You have to initialize it. So we'll initialize our new parameters to be the same as the old parameters at iteration I equals 0. So that means this KL term will disappear because our new belief is the same as our old belief, right? We have to start from somewhere. So we're left with this objective function that's just the expected log likelihood. So if we do if we only do one step of updating, of iterative updating, then we can ignore this KL regularizer, and we can just use the fact that we're just going to do a little bit of optimization so that we don't overfit, and we don't need that penalty term anymore. So we call this the Bayesian online natural gradient method, Bong, and this is the first ingredient of our Bong method, which is a paper published at NRIPS last year. So basically, from this view, it's a special case of BLR where we just do one update. So pictorially, we have our prior, and we go in one step right here to our new posterior, whereas BLR will take many, many small steps. And because it does many steps, you have to regularize them so you don't overfit. But if you just do one step, you get implicit regularization. Okay, so that's the first step in Bong. And how does that relate to vanilla gradient descent that you're probably more familiar with? Well, in vanilla gradient descent, you just say the new parameters are the old parameters plus the gradient of the log likelihood. So there's a few differences here. First of all, what you're estimating are the parameters of, let's say, your neural network, theta, whereas what we're estimating are the parameters of our variational distribution. So we're optimizing over mean and variances, whereas this is optimizing over the weights of a network. So there's no notion of uncertainty here. It's just a point estimate. And we'll need uncertainty when we get to RL and decision making, that I will get to eventually. Also, this is just regular gradient descent, and it's statistically quite inefficient, so it might need many, many, many passes over the data. Whereas if you do things in a Bayesian way, it's the optimal estimator. So you only have to see each data point once. So it's very good in the sparse data setting. So the difference between vanilla online gradient descent is that's the upper equation, and Bong is this lower equation. So we're optimizing different parameters, and we're using natural gradient instead of vanilla gradient. And we're modeling a distribution instead of a point estimate. So there's quite a few differences. But we can still compare to OGD as like a baseline, which we will. All right, so now we have to, so that's the high level. Now we have to compute these equations. So we have to compute the update step for the variational parameters. So in the case of Gaussians, the new mean is the old mean plus this expected log gradient term, or gradient log term. And then the new precision is the old precision minus this second order matrix term. So we have to compute the gradient and Hessian, and that is our new computational challenge. Okay, so for the gradient, a standard thing that people do, like in the BLR paper, they just do Monte Carlo. They just sample from it. They compute the gradient of the neural network, and to compute the expected gradient, they just sample from the distribution and evaluate each of those gradients in average, right? So it's a very simple estimator. But it might need a lot of samples to be reliable. So we use a different trick. We linearize the model, like in EKF, and in that case, you can compute the gradient analytically. So it's like fully deterministic. So that's the gradient term. And in the Hessian term, it's the same kind of story. So we can compute the Hessian of the neural network in principle. And if we want the expected Hessian, we could sample and then just call, Jacobian or whatever 100 times. But that's going to be pretty slow. So again, we linearize, and then we can compute everything analytically. So that's a choice we make. So it's like a bias variance trade-off. It's a biased approximation, but it's zero variance because it's deterministic. And in general computing, second order matrices is expensive. So it's very common to use this empirical Fisher approximation where you approximate the Hessian as the outer product of the first order gradients. So again, in prior work, people use Monte Carlo estimates, and we use our linearized estimates. So that's how we compute these expressions, and then we can use them to update our parameters, our variational parameters, and this is the last sort of degree of freedom we have. Like, what are the variational parameters? So we could just work with the full mean and covariance, but if we're fitting a neural network with 1 million parameters, the covariance matrix is 1 million times 1 million. So it's pretty big. So we can't even store it in memory, let alone compute it. So we're going to need some approximation. So a lot of prior work has used a diagonal approximation, but a diagonal approximation doesn't capture the correlation between the weights, and it's really no better than just regular gradient descent, point estimation. So this, it's a waste of time, basically. It is fast, it's linear, but it's really not much better statistically. So what we did is to use a diagonal plus low rank approximation to the precision matrix. So we have the diagonal, and we can choose how many, it's like PCA. So we choose a low dimensional subspace to represent the covariance matrix of this Gaussian. And we're going to update the low rank factors W. And so this representation is called DLR, diagonal plus low rank. This has been used in prior work, but it's the way in which we perform the updates is novel, and we called it lo-fi, low rank filtering. And we have some ongoing work with Gerardo that is a variation of this where we do low rank on the covariance matrix plus some other tricks that I'm not going to talk about today because they're not published yet. But anyway, there's a lot of games you can play here. But this is sort of the family, the variational family. So focusing on lo-fi, because this is the published work. So we have our prior. We push it forward through the dynamics, which is straightforward, as I talked about. We do the update, which involves solving that optimization problem I just talked about. And then what happens is the low rankness is we've just lost it, right? We were rank 10. We condition on some data, and now we're rank 11 or rank 15 or something. So we're no longer low rank, or not as low as we want to be. So we project it back down to our chosen variational family, and for that we use SVD. So basically lo-fi, I think I have the pseudocode. I'm not going to talk you through it, but it's basically EKF plus SVD at the end of the day. So it's computationally very fast, and it's all closed form, and it's like, 10 lines of JAX. It's just beautiful. Okay, so does it work? Yes, it works. So here's a little demo. This is that 2 moons data set again. The data streaming in, and then you can see the decision boundary. This is a point estimate of the posterior mean. And then the contours represent the predictive distribution in data space, which I think in this case, I don't remember how, it might be a Monte Carlo approximation. Maybe it's numerical integration because it's 2D. And then here we're estimating the accuracy of the classifier online, and you can see it converges to whatever the maximum you can do is with this model family. And then we applied it to MNIST, so this is not like Google scale, it's an academic project. So this is misclassification rate versus number of data points. And here we're going out to like 2,000 data points. So we're really targeting the small data regime where data is scarce. And the motivation is that we're going to be collecting our own data, which I'll get to in a minute. So we really want to squeeze as much juice out of it. We're going to treat data as a precious resource, not as an infinite resource, right? We're not training on the whole internet, right? I want to be careful about the data that I use. So our curve, the Bong is the black one, and we converge faster than all these other methods, including, I won't talk you through all the variants, but you can read about it or ask me later. And we get it's not just a point estimate, but we get a posterior, so we can measure how calibrated we are using something called the expected calibration error. And I can't even remember. I think we're Bong with the bottom right. We are more calibrated than alternative estimators. Okay. All right, so that's it for supervised learning. Any questions at this point? And now I'm going to talk about decision making. Yes, please.
Bong, how many hyperparameters has to be set as compared with the regular set?
Good question. So basically, there's the Q term, which is like the drift parameter of the noise of the parameters. So that's often 0 or some small constant. And then there's the initial prior belief state, which is just like, so we sample that from like a LeCun normal distribution like you would when you're initializing a neural network. And then the critical parameter is what's the initial covariance matrix, because that's like the regularization factor if you do lasso or ridge regression or an L2 penalty. I mean, it's exactly the same as that. So that's just the degree of regularization. So truth in advertising, we, like many other people, tune that regularization parameter offline using a validation set, which violates the spirit of YOLO, you only live once, and truly online. So you can do it truly online. You just treat your noise parameters as additional variables in your Bayesian model, and now you have a hierarchical Bayesian model. And it's not Gaussian anymore, but there are tricks you can play, like particle filtering and Rao-Blackwell-Ice particle filtering, things that various people in the audience have worked on. And that's actually something we're doing now, where we plug Bong as a subroutine inside of this larger, bigger Bayesian model, so we can do everything online, and there's no validation set anymore. Because when you have non-stationary distributions, it doesn't make sense to define a test set, there's just a data stream. That's all you have, right? So anyway, so there's slightly more parameters than a typical neural net, but not many. All right, let me move on. I did promise to talk about decision making. So supervised learning is not, I mean, there is a decision, it's like what the class label is, but the data is just coming at you and you're just absorbing it, you don't control it. So now I'm going to talk about settings where you can control the data. So I'm not going to get to full RL in this talk. This is like a baby step towards RL. But this is a very special case of RL. So this is called the bandit problem, where you can choose k possible actions. So why is it called a bandit problem? So in vernacular English, a one-armed bandit is the name for a slot machine, like if you go to a casino, and you can pull the arm, and then the wheels spin, and you get some payout. Maybe you get 80 cents, maybe you get $1.50. You don't really know. So you keep pulling the arm, and then you try to estimate, what's the payout rate of this slot machine. But it's a multi-arm bandit because there might be many slot machines, and you can go pull the lever on all of them, and you're trying to find the one they call it the loosest slot, the one that pays out the most, or the most reliably. So maybe this is actually going to give me $10. But I don't know yet, because I haven't tried it. So the key thing about this setting, unlike supervised learning, is you choose what to do in the world. You have to pick an action, and that controls the data that you receive. So it's called bandit feedback. It's partial feedback. You only get feedback on the things that you do. So if it's a new slot machine over there, I got to go try it. So this is a mathematical model. Nobody's really using it for gambling, but it actually has an incredibly large number of applications. So the actions could be, in a clinical trial, I have 3 possible drugs. I've got placebo, I've got drug A, drug B, and I want to know, it's like an A-B test. I want to know what the best thing is. Well, I could give drug A to this patient, and maybe they recover, and then, but maybe I got lucky. So then I should probably give it again, right? And maybe the second person gets sicker. And so there's going to be some stochastic feedback from the environment for drug A, but I need to know about drug B as well. So, maybe A looks really good, but B might be better. So I have to balance, I'll talk about this more later, but the exploration problem where you're trying new things with the exploitation problem where you're using your knowledge to try to maximize reward. So here the objective function is to maximize the expected rewards you receive, right? And this reward model, if it's, whether a patient recovers or not, it could be binary feedback, so a Bernoulli bandit, or it could be a real valued thing like, what's their temperature or morbidity rate or whatever. But so there are a lot of applications in medicine, a lot of applications in e-commerce, right, for advertising. But I'll come back to that in a minute. So if we visualize that as a graphical model, what's going on is that there is an unknown state of nature, theta, which are the parameters of this reward function, which you can think of as just a vector of the payout rates of the k different arms. It's just a k-dimensional vector. So we don't know what it is. And at every step, we pick an action, and according to our policy, and then we observe a reward, and then we're going to be updating our beliefs about this unknown parameter, just like we did earlier with supervised learning, but now we're controlling the data. And the policy is going to tell us what arm we should pull, and that will affect the data we receive, and when we receive the data, we just do the Bayesian update that I talked about. So the action is the policy is a function of the history of previous data that we've seen. So the history is the previous actions and rewards. This is the reward model, and our policy will be some function of this belief state. So I'll talk about that in a minute. But the key thing is we don't know the payouts of the arms, right? So the theta parameters are unknown. So we're going to recursively estimate a belief state distribution over that. And if it's Gaussian, we can use Bong. That was the whole point of the last half an hour. And when we have that, then we can use that belief state to design policies that will be optimal. Okay, so that's bandits, multi-arm bandits. Now, there's a slight generalization that increases their usefulness tremendously, and that's called the contextual bandit. So it's exactly the same setup, but now at each step, we also observe a context vector, S, or a state vector. And we can choose an action to maximize our reward, and the reward depends not only on the action, but also on the state. So for example, you might visit a web page, and that web page is, has some, it's a soccer page, it's some sporting stuff, and you have, 1,000 possible ads you could show. Well, the ads that but you only want to show like 5, because there's not enough space on your cell phone screen. Then you want the ads that you show to depend on the state, which is the content of the web page that you're viewing, Or maybe you have some information about the user. You know they're a sports fan. And then if they go check some political news, you would show them different ads, right? So the action that you take will depend on the state. But you don't know what they're going to click on, right? So you're trying to maximize revenue. This is what Google does. This is how we make most of our money, and not just Google, but all the e-commerce companies. So you want to estimate the mapping. So it's going to be, now it's going to be a mapping from features to rewards, right? So it could be a linear function, but it could be a nonlinear neural network. So just like we had before, where we had supervised learning, we're mapping features, S, states, to outputs. But they're also controlled by the actions that we take, right? So if I show you an ad that's relevant to this web page, then you're more likely to click on it. If the ad's completely off topic, then I'm not going to click on it, and I didn't get any reward. So we want to learn this reward function, and we want to show ads that will discover what the user is interested in. So that's the explore problem. And then once I know, I want to show you them, so you'll click on them, I'll make some money. So that's the exploit problem. So that's contextual bandits. It's also used in clinical trials where you have, it's the same drug problem we talked about before, but now you know something about the patient before you give the drug. So that's the state vector. And then connected to RL, just a second, Nano, this is a special case of a Markov decision process, or a POMDP actually. But now the state vectors just arrive according to some random process, and you don't control it. So your actions affect your beliefs about the world, but they don't affect the state of the world. If we put arrows on these S's, then the states evolve over time, and then we get a Markov decision process, and everything I'm saying becomes harder. But did you have a question?
No, just a remark. What we do now in our LHF is also when we only have outcome rewards, which is most. Yeah, so approaches like O1 maybe not public, but DeepSeek. Yeah. And so on, they all do the same thing actually as this, because typically no one uses process rewards, but outcome rewards. Yeah. So it's just one step. So S is a prompt, A is the answer, which is a sequence of tokens. So the action is a whole sequence of tokens, and then you're trying to optimize some outcome reward. Yeah, no, but most of what people think of RLHF these days and talk about as RLHF is actually this.
Yes, I should have I would have made it sound all sexier, right? So you can apply, this actually does apply to LLMs. It's exactly what this is Nando de Freitas was just saying. What they call RLHF, it's not really, there's really only one action, which is like, let's say it's a math problem. It's the final answer, and you get one piece of feedback. It's 42. Did you say 42, yes or no? And then you get the next prompt from the user, right? So it's not really a sequential decision problem. It's just the action space happens to be a sequence of tokens. But there's no interaction with the environment. It's a one-shot problem. So RLHF, for most current applications, including all of the thinking models, are actually bandit problems, contextual bandit problems. They're not real RL problems. Now, when you do multi-turn RL and you interact with the user and you do tool calling and you get feedback, then it's full RL, multi-turn. But I'm not going to get to that today. I'm talking tomorrow in the RL workshop, but that's separate work. Okay, let me keep going. So this is contextual bandits. I talked about explore, exploit. Okay, so how are we going to solve this explore, exploit problem? This is sort of the core problem. How do we decide what to do when we don't know the true state of the world? Well, one thing you could do is there's a common heuristic called upper confidence bound. It's very intuitive. It just says, pick the action that you think is most likely, but give yourself a bonus if you're uncertain. It's called an exploration bonus. So you can imagine drawing a distribution over the rewards for each of the possible actions. So if it's like a Gaussian, you've got your mean. So I think this green thing is good, but there's some uncertainty represented here. This red guy, doesn't look as good, but I'm really uncertain about it. So maybe I should try the red guy, and then I'm going to learn something, right? So this is called the UCB heuristic. So critically, to implement this method, you need not just a point estimate of the parameters, but you need a notion of uncertainty. And that's why it pays to be Bayesian, right? Because now you can implement this algorithm, and this algorithm is provably minimal regret. So it's an optimal algorithm. But there's other algorithms that also enjoy optimal properties. So Thompson sampling is another such method that is easier to apply and works well empirically. And it's very simple to explain. So you have a belief to state, you draw a single sample from that, you plug it into your model, and then you just greedily pick the maximum, the best possible action. So you sample and you exploit. You sample and you exploit. So it's computationally very simple. So now all of sequential, well, not all of sequential decision making, but all of these bandit problems, this is a trivial policy, right? I don't have to learn any parameters. All I have to do is do online Bayes. Okay, but I just spent half an hour telling you how to do online Bayes. So you just take all that stuff, you stick it into Thompson sampling, and lo and behold, you have a provably optimal estimator for contextual bandits. So a little more detail, like if we have k possible arms for the discrete actions A, then our likelihood will be, we can assume that, say, we have a different belief state for every arm. We don't have to assume that, but we can have a factored prior. The likelihood we only get feedback about the one arm that we did or the one action that we performed. So if the prior is factored, the likelihood is certainly factored, so the posterior is factored. So you can just update each of the parameters one by one. And the ones that you don't collect evidence for, you don't change your belief state. So this update function is Bong or BLR or EKF or particle filtering, whatever, right? That's just a subroutine call. And so you just plug it into Thompson sampling. It's like 2 lines of jacks. So it's all very beautiful. And it works. So this is a little toy problem where we converted MNIST classification into a bandit problem. So instead of getting the true label, you're just told whether the label you picked is correct or not. So it's binary feedback. So there's 10 possible labels, 10 possible arms I could pull. And if I get the arm right, then I get a reward of 1. Otherwise, I get a reward of 0. I think in this case, we use Gaussian reward, but you could use Bernoulli reward. And our method is in blue. This is lo-fi that I talked about earlier, plugged into Thompson sampling, and it outperforms other approximate Bayesian methods, and it also outperforms like epsilon greedy. 10 minutes, okay. So here's another application which is very similar. So you can think of Bayesian optimization as like an infinite multi-arm bandit problem. So essentially the arms are the input x to this black box function, and I'm trying to find the arm that maximizes the function, right? Which is like the slot machine that pays out the most. But now the arms are parameters of some unknown function. So these could be hyperparameters of a neural network. They could be a molecule that I'm designing, or a protein sequence or something. And this f function is a black box. It could be a weather simulator. It could be a wet lab experiment. The assumption is this is expensive and it's gradient free. So I want to be very careful about what experiments I perform, right? Because each experiment is $1 million or something. So I can do 10 trials, and then I have to make a decision. So Bayes opt is closely related to bandits, and not surprisingly, you can use the same kind of machinery to solve it. So one thing you could do is very common to represent your beliefs over functions using a Gaussian process, and I'm not going to go over that today, but you can combine Gaussian processes with the UCB heuristic, and that's a common method. But we want to use neural nets, right? Neural nets are much more flexible. Oh, this is a figure from Nando, actually. I should have given you credit. So this is a little illustration of how Bayes op works in 1D. So there's a true function, which is the black line, and you observe this data point here and this data point here. So your uncertainty about the function at these 2 locations is 0, right? Because you've seen the ground truth. But you don't know what the function is in between, and you're trying to find the maximum of this. So you can choose where to probe it, like what question should I ask next? So here, there's something called an acquisition function, which is like the UCB heuristic, and that says, okay, I should pick the point here because it might not be the highest, but I have a lot of uncertainties. It sort of trades off, just like we did earlier, right? The mean and the variance. So you go there, you get an observation, you update your belief state, and so on. So as you probe the world, you get data, you update your belief, and you keep experimenting. Okay, so that's Bayes op using Gaussian processes in UCB, but you can solve the same problem using neural networks and Thompson sampling and approximate Bayes. So that's what we did. So the unknown function is represented by a neural network instead of a GP, and the belief state is represented by a Gaussian, and the update step is Bong. And then actually, it isn't quite Bong. This is a very, very recent slide. So this is a new variant of Bong that's even better. And so it's unpublished work, so it's just a teaser slide. Stay tuned for the NeurIPS deadline. But there's an unknown function, which is this wiggly red line. And we estimate it with the black line, and we have 1 data point, so we're terribly off, right? But we interpolate it, and then we observe a few more data points, and we interpolate it. And what we're observing here is the output of approximate Bayesian inference applied to a neural network, and it looks just like a Gaussian process, but it's a neural network, so it's going to scale much better. And this is the best results we've ever had, so we're really excited about this. Like, it looks like we're actually getting Bayesian neural nets to really work finally, and it's strictly online, no batch, so very excited about this. But we'll see how far we push it. And then there are related problems like experiment design that I won't talk about today. Okay. Maybe I'll squeeze in this last thing. 6 minutes, 7 minutes, sure. Okay, so everything I said so far is sort of, it's the standard Bayesian paradigm with approximations that we make so it goes fast. Variational approximations and then linear algebra tricks, SVD, low-rank tricks, plus AutoGrad. There are just a few tools in the toolbox. Now, there is a problem with Bayes, which is that if your model is wrong, it's optimal, but only if your model is correct. And your model is always incorrect. So we would like to have a method that's a bit more robust to misspecification and outliers and things that we didn't model properly. So as an example, imagine this tracking problem we saw earlier. Imagine that the observations, you might observe the location of the plane, but occasionally you just get random noise, right? There's like a bird flying by or your sensor breaks. So you get these noisy measurements. Well, then if you apply Kalman filtering to it, you get this crazy state estimate. This is the green line here. You can see it's very sensitive to outliers because we assumed it was Gaussian, but in fact, the true generating process was not Gaussian. In this case, it was a student T. So we'd like to be robust. That was the linear setting. This is something similar. We saw this before. It's a nonlinear model, but now the measurements are contaminated with outliers, and we want it to still work, right? Okay, so how are we going to do that? Well, previously we talked about variational inference, which is optimizing the expected log likelihood plus this KL regularizer. Well, so there's a very beautiful thing called generalized Bayesian inference that basically says, let's just replace log likelihoods with arbitrary loss functions, and let's replace KL regularizers with arbitrary divergences. And then it's still an optimization problem. It's a much larger class of methods, and it is clearly more general than Bayes, but you're still optimizing over distributions, but using a different objective. So there's a very nice paper on this called, by Jeremias Knobloch, who's a professor in London, I think UCL. It's called an optimization-centric view of Bayes' rule. So it's like a 100-page long JMLR paper. But if you like this stuff, you should go read it. It's just very beautiful. So we collaborated with him on an instance of this setting where we're actually going to keep the KL regularizer like we did in Bong, but we're going to replace the log likelihood with a robust loss function that will make everything I said work better even if there are outliers. And it's a super simple method. So suppose we have a Gaussian likelihood. What we're going to do is replace it with a loss where we weight the observations by a weighting term that we can choose, and this is going to downweight things that look like outliers. For example, we could choose this. In the online setting, we can make this weighting function be adaptive, right? So I want to know what weight I should put on the data. Well, I have a prediction about what I'm going to see, and I can compare my prediction to the truth, and if it's unlikely, I'm going to put less weight on it because I don't really trust my model. So if I put that weighting function and I combine it with my log likelihood, then you can show that in the linear setting, you can compute the generalized posterior using a very small tweak to the standard Kalman filter where you just downweight your observations, the observation noise with this weighting term. And then you can apply this to nonlinear models by combining with EKF, and then it plugs into Bong, and everything works. It's all modular and lovely. And does it work? Yes, it works. So we call it, this is called an inverse IMQ, inverse multi-quadratic kernel. It's a standard kernel in the literature. So this is the example earlier. This is standard Bayesian inference, and this is generalized Bayesian inference, where we add that one weird trick where we just robustify things. And you can see it's a much better estimate. And you can, in the 1D case, Kalman filtering, the exponentially weighted moving average is a special case of the Kalman filter. So you can robustify it, and now you can have like this robust online estimator of signals. That's like a special case of this method I described called WILF. So that's a cute application. And then, of course, you can apply it to nonlinear models using all of the stuff I talked about earlier. So here's a nice smooth estimate of our neural network as the data streams in, even though it's contaminated with outliers. And we didn't have to model the outliers. So it's super fast. And then we did some bake-off where we compare error versus running time, and we're in the lower left, so we're fast and we're low error. And we beat other methods that I won't talk about. Okay, I actually finished. All right, so just to summarize then, so I talked about sequential Bayesian inference, and I gave some applications, online learning of classifiers, bandits, Bayes opt, and I talked about how to make it go fast using low-rank approximations and variational inference. And in the future, the goals are like, now I think we've sufficiently fine-tuned the methodology that we're ready to scale to like transformers and big models. I think the peak model we fit here, mostly due to the fact that it's an academic project running on Colab, it was like a 1 million parameter CNN. But you know, I think everything's linear, so it should just scale to 1 billion parameters. So if someone wants to work with me on that, come talk. The examples I gave were mostly stationary, but all of this works for non-stationary environments, which is the original motivation for this work. And then the killer app is RL, reinforcement learning, which is inherently non-stationary because you're changing your policies, so you're changing the data that you collect. And like multi-agent RL is even more ambitious, right? Because you're competing with or potentially competing with other agents. So everything's very non-stationary, and you've got to adapt very quickly. So I think this Bayesian stuff that is the killer app for all of this machinery. But that's future work. I am talking tomorrow in the RL parallel session, but not about Bayes. I'm talking about model-based RL. So thank you.
We have time for a couple of questions, maybe? Yes. Oh, you want the mic? Yeah.
Many thanks for your inspirational talk. I'm right here. This way. No. Closer here, this way.
Yes,
Hi.
okay.
I have a question on this generalized variational inference, in which you can replace like yes, this one. You can change the log posterior by loss function, regularity, divergence. I have some questions. What happens? Do you have any guarantees for what you get in the end will be the true posterior if you change the log by some arbitrary loss function?
It's not a posterior anymore. It's not a Bayesian method.
It's not.
It's a more general class of methods that enjoys a lot of optimality properties that Bayes does, but it has advantages. It's more flexible.
It's more flexible. Okay.
So actually, this guy Knoblauch, if you're interested in this area, and I think it's super interesting, especially if you're like theoretically inclined and have like a stats background, this is a great field to work on. He's running a webinar series right now called Beyond Bayes. So there's a whole class of methods that are sort of Bayesian inspired, but recognize the limitations of Bayes primarily due to model misspecification, and then build on this generalized VI setting and other related methods. So he's got some nice tutorials online, so check it out.
Okay, thanks.
Hey, here. Is there any way to adapt like the reward solution to take into account future rewards? Like if you have 5 coins for the slot machines and you know that one machine is gonna pay up if you put 5 coins into that, is there a way to adapt to like take into account future rewards?
Well, you don't see the future, right? So in this setting, the likelihood function is a function of your current observation, right? So we can weight the current observation given what we've seen, but we don't know the future. Now, you could anticipate the future and plug in, predicted future observations, but ultimately you don't know them, so you're going to marginalize them out. So you can only be a function of the past. This is a causal system, right? Maybe I misunderstood the question.
I thought we were predicting like the next occurrence.
Yeah.
So like if we predict even further into the future, we can like analyze more. If we know we're gonna have like 5 chances.
Oh yeah. So I think there's 2 things you're saying. We're predicting a distribution of an output, so we could sample from it many times, and then we could do best of k, which is I think what you're talking about, and maybe only one of them has to be correct. But another way of getting multiple chances, I could predict multiple steps into the future, and then predict a batch of future outcomes. So multi-step forecasting. So that's straightforward. So you can do both of those. Is that what you're asking?
Oh, yeah, yeah.
Okay, thanks.
Hello. My question is not about the recent work that you are doing, but in general for RL. Will Thomson sampling and UCB work in the full RL setting or just bandits? Because my intuition is that if you change the policy, the distribution of rewards that you get changes. So I have a feeling like maybe those will work only on bandits, but not for full RL.
Sorry, where are you speaking from? Oh, I see. Okay. Yes, you can make it work for full RL, but it's easiest to do in the episodic setting. So there's something called posterior sampling RL, where basically at the beginning of each episode, you sample parameters from your belief state about the underlying MDP. So here, the only unknown is the reward function, but if it's an MDP, there's also dynamics, right? It's the same machinery. It's exactly the same thing. You sample from that, and now you greedily exploit with respect to this MDP, which itself is a hard subproblem, right? But you could do, value iteration or whatever, run a standard RL algorithm on your current belief, and you exploit that for the current episode. And then when the episode ends, you update your belief state and you repeat. So then across episodes, you'll explore, and then within an episode, you'll exploit. So you can make it work for full RL. People do that.
Okay. Thank you.
Yeah. Let's thank the speaker again. Thanks. So next we have two spotlight talks. The first one is from Cesar Beltrán from the Pontificia Universidad Católica del Perú. Cesar is a full professor and senior researcher at PUC, Department of Engineering, Computer Science. He's a doctor in bioinformatics and master's in computer science from USP São Paulo, Brazil. Postdoctoral stay at Texas A&M University. He was chair of the IEEE Peru section and president of the IEEE Computer Society in Peru, founder and scientific leader of the Artificial Intelligence Research Group at PUCP.
Good morning. It's a challenge to make a presentation after Kevin's presentation. Okay. But I have a question for you. Thank you for the invitation. Nice to stay here. After 10 years, I come back to Chile, and it's grateful to stay here. Okay, congratulations to the organization of KHIPU. Okay, I have a question. Which is the most important event in AI? And when, for you, for example? We are all the family in artificial intelligence in Latin America, okay? And for us, which do you believe is the most important event? Transformers. Invention of the digital logic. Okay. Another? Kevin, for you? 2012? AlexNet. Okay. And 22, 23? In 22 and 23, we had two important events. Okay? The trilogy of Kevin. And 2012 too, okay? These are important books for us, all the people who are studying artificial intelligence and machine learning, okay? For my university, which is the most important event in AI research, in my university is 2013, the foundation of my group, okay? Of my research group. And we started our research in 3 lines. bioinformatics, computer vision, and natural language processing. And recently, we are starting to work with graphs too. No? Yesterday, we have presentation on graphs, and it's everything is connected, okay? And it is important research line that we are starting to work to. We are awarded with very grants and funding, okay? All research group lives with the grants. Okay, we have grants from our own university, from national university, or from national funds from Peru, and international funds. During the last 10 years, we awarded with approximately $5 million in grants. We are connected with several universities, with several research laboratories in the world. Okay, we always are traveling to another countries to do a similar work. Okay, this is the line of the evolution, no, especially from the computer vision. Okay, we started from basic detection to deep learning that we are living now. Okay, all the people that we work in artificial intelligence, especially in computer vision, we started with the process of feature extraction. Okay, the manual feature extraction process, and now we use the convolutional neural network for the feature extraction. And we started with different kind of projects, especially applications in different areas using artificial intelligence. Or especially, I work, for example, in computer vision, and my line of research is the use of computer vision in different applications. For example, we had this project in biodiversity conservation through a computer vision application, okay? And we have some results. We use the classical techniques for computer vision. And another project that we had, for example, was the micrographics image processing for the automatic evaluation of male fertility. And in the same way, we have some other publications. We worked with the automatic diagnostic of the coffee roast disease. And another area of research is the natural language processing with another group on my team. Worked in the machine translation, especially in indigenous language. And this group was very, very interesting, and they produced many papers. Okay. Another application, for example, was the NLP application in Spanish, with many other publications too. Okay. For example, we worked with Ivan. Ivan Cipiran was one of our members. Now Ivan is working here in Chile, in Universidad de Chile, and he works in 3D object reconstruction, especially application in archaeology. Okay. And in this moment, in 2017 approximately, we started to use the convolutional neural networks. Okay. For example, we started the deep learning era. Before 2017, we use generally the classical techniques of computer vision using the manual feature extraction. And we had two initial papers. For example, this project was developed using a simple convolutional neural network, similar to the LeNet classical neural network or classical convolutional neural network. And Ivan used the generative adversarial neural network to reconstruct archaeological 3D pieces. And we faced with convolutional neural networks, and we said, wow, it works. No? You don't need to do or to extract manually the features. Okay? Then I think we have already found a solution. Okay? And we started CNN is all you need. Okay? Do you remember our project about male fertility? Take that image and use a convolutional neural network. Do you remember a document, digitalized historical documents? Take that database and use a convolutional neural networks. We need to classify the clouds for a project that we are starting to do or to work with the CENAMI, is the Meteorological Institute of Peru, and then use convolutional neural networks. Do you remember the data set of parasites image? Apply convolutional neural networks, all convolutional neural networks. But convolutional neural networks have several limitations. You know, okay, that the convolutional is not the holy grail of the computer vision, no? Okay, and then we started to use another strategies, not only convolutional neural network. For example, in this project, we faced it with several challenges, including limited satellite image data, varying resolution across sensors. For example, different satellites has different resolution, okay, and insufficient labeled data. For example, in this case, we faced it with many problems. The idea was to segment the areas with the fluid is represented, or the water body is represented in the image, in the satellite image. Okay, this is our image, and this is our labels. Okay. The idea is very simple. Okay, you have to segment that fluid areas, but we face it with super resolution problems. We face it with different size of the image, and so on. Okay, and we started to work in this kind of problems, and we obtained many other publications. Okay. Recently, we started to work with graphs. Okay, and we are working with the Laboratory of Genomics in my university. And we are using a graph embedding, exploratory analysis of mass spectrometry data based on graph embedding. No? And the idea is, only 5 minutes, okay. The idea is that the mass spectrometry generates complex, high-dimensional data that can be challenging to interpret using traditional methods. Then we are using graph embedding to work in this problem. Okay, we have two papers published the last year. Okay, we have, for example, 2 of the graphs here. When you have a mutant in one of the nodes of the graph, okay, what is the consequence of the mutant? And we face it with many different problems here. For example, to compare 2 graphs, the similarity of 2 graphs, how can we do? We generate the embedding of the graphs, and we try to compare this similarity only comparing the embedding vectors. During these 10 years, we have over 100 publications in conference and 30 in journals. We received over $5 million in funds, and we managed about 30 projects. Okay, and we participate in many conferences. For example, we have the visit of Jean LeCun. We organized the SHARP conference in Lima in 2016, and one of our keynote speakers was Jean. We faced it in Andrew NG. Andrew NG, well, I know in NeurIPS the last year. Okay. And since 2018, our university is considered within the QS World Ranking by subject in computer science. Okay, in the last ranking of the 2024, we are in the position 18 in the Latin American universities. And many of our members studied postgraduate, and they are working in many other laboratories in the world, okay? There are only a list of some of them in important laboratories in USA, in UK, and in other countries. And we have two programs of professional specialization, one program in data analytics, and another program in artificial intelligence, okay? A successful program because we are in the 12th edition that started the last month. All is online, okay? This is part of one activity that we did in January, okay? We call it the summer camp in artificial intelligence, okay? We call for the people that want to work for 1 week with us. We select the curriculum most important, and we select only 40 people to work 1 week with us. This is my group, okay? And thank you for your. Okay.
Thank you, Cesar. So our next speaker is Juan Matias Di Martino. Juan Matias Di Martino received his Bachelor in Science and PhD in Electrical Engineering from Universidad de la República in Uruguay. From 2016 to 2017, he was a research associate with École Normale Supérieure in Paris. He worked at Duke University as a research assistant professor in the Department of Electrical and Computer Engineering. And he's a full professor at UCU and an adjunct assistant professor at Duke. He published over 50 peer-reviewed scientific articles and led several large-scale research projects. He contributed as a key personnel to secure over 50 million of research funding and worked with companies to translate research into production deployments and products. His main areas of interest are artificial intelligence, machine learning, computer vision, and image processing. Thank you.
That was not my fault. I'm going to use this one. If we have the other microphone, I would rather move across. So if I can. This is off. Let me use that one. Can you hear me well? Great. Thank you for inviting me. Thank you, Chile, for receiving us. This is my second time. I came here in November for La Coro, a summer school in robotics, and I'm blown away by the academic community here in Chile. I spent a couple of years working around the globe, and I recently came back to Latin America. So coming here and see that there is this level of research in Latin America is really makes me pretty happy. I'm now working in Uruguay, and I'm collaborating with some other international places, but I'm mostly based in Latin America. So I'm going to show you some of the work that we're doing, and I'm open to talk to you if you're around as well. This is a short talk, so I picked one of the research projects. I've been working on this for the last couple of years, and we recently got some exciting results, so this is what I picked to talk to you about today. And at the end, if we have time, I'm just going to very briefly in one slide tell you about the other projects, just to prime you with the figure, and if you are interested in those, we can talk offline, but this is a short talk, so bear with me, I'm going to talk about this one. This project is about early screening for autism using computer vision. It's a project that I'm having the pleasure with collaborate with two great collaborators. Sherry Dawson is professor at Duke University. She's the expert on autism. And then Guillermo Sapiro, who is at Princeton University and is actually here at KHIPU. You may see him tomorrow, I think, in some panels, and he's sitting somewhere over there, so you can talk to him as well during this meeting. And so let's start with why we need to work on a tool to do a screening for autism. Estimates when we started this work was that autism prevalence was around 1 in 50 kids. The last estimates that I got was that the prevalence of autism is 1 on 30 kids. And there are a lot of, it's very common. But the current approaches that we have don't scale. For example, in North Carolina, where I was living, if you think your kid might have autism and you go and want an expert to do an assessment, the wait list is months, and we're talking about a place that had great healthcare. If you go to other places, the problem is it's a lot worse, and we had a talk on Monday showing how access to healthcare in Latin America is also critical. So the way we're doing it just simply doesn't scale. We need to develop technology to get healthcare closer to people. And why we need this now and why we need to do screening early, there is a lot of robust literature, including some from our collaborator, Jerry Dawson, that if you can detect autism when the kids have 18 to 24 months and you can start giving them the support tailored for their needs, then after 2 years, if you compare with the control group, there is a difference of plus 10 IQ points between the kids that received the specific treatments and the kids that did not. And these 10 IQ points might not seem like a lot, but this is a huge deal. This could be the difference between being able to get a job or depending from your caregivers and need support. So this is a huge deal for this population, but this works if we detect this early. We cannot be detecting autism at 3, 4, 5 years old like we're doing right now. So what we propose is to develop technology and use an app. We created a bunch of movies with experts in autism. These movies have social and non-social components. And what we do is we show the movies to the kids in iPads and iPhones, and while we're showing the movies, we capture we record them with a frontal camera, and using this video, we detect a lot of behavioral phenotypes that we call, and I will show you some examples. So using this approach, we check how they respond to the name call, we check their facial expressions, you check the social attention, and we do all of this with devices that we already have at home. So let me show you how some of the data looks like. So there is a lot going on in this slide, so let me walk you through it. What you're seeing in the left side, you're seeing the video that we're showing. So here in this particular stimuli, there is 2 people having a conversation. This icon shows you who is talking at this given time. So in this stimuli, you see now the person on the left is talking, then the person on the right. What you see in the center is the video that we recorded. And of course, I cannot show you the actual face of the kid, but you can see the details of the face, and you can see the eyes, so you can actually extract gaze and facial expressions, the head pose, and others. So you can see, what you can see here in the middle is the facial expression that we're estimating, and this is a long time series. We had that estimation for each frame. What you see on the bottom is the head pose, is the 3 angles of the head, and what you see here in the bottom left is the gaze. In red, I'm showing the accumulated gaze throughout the stimuli. So you can see this person is looking at the 2 faces. The gaze is 2 clusters, pretty concentrated. And then what you're seeing in the blue dot is the gaze for a given frame. So this person is switching between the 2 people talking. This is a neurotypical kid, and this is what you would expect the gaze to be. When you look at these patterns for kids with autism, the gaze looks very different. It's scattered across, and the coordination with the people speaking is a lot less. So we use this data, we collected data on over 1,000 kids, several hundred kids with autism, and this is a very high dimensional data, so we took an approach where we compute these features. We propose different biomarkers that we call them, and so let me show you an example of some of them. So we propose biomarkers across these 4 different domains. They include how they respond to the name call, how their gaze patterns are, how their head movement and facial expressions evolve, and how their coordination and touch using a game at the end. And this is necessary because autism is a very diverse manifestation, so you cannot just use one tool and pretend to characterize everybody. So you really need to work across these different domains. You can see the details on these publications, and I'm going to show you one in the interest of time, just so you get an idea. And let me show you, for example, how we detect how the response to the name call. So what you see on the top is the video, and we collect this in primary care settings, so there's no gaze tracking, non-specific hardware. We just have the iPad in the primary care visit. This is pediatric standard clinics. And so during one of the videos, we call their name. You can see the research assistants on the back calling the name, and you can barely more or less see the kid turning around after the name is called. And this is something that experts on autism already know. They know that there is a difference on how often kids respond when they call their name, And we started with this because it's a very robust biomarker when they do the assessments. So we started by making this automatic. We use the head pose and we use the audio to detect both the name call and the head turn. And these are some of the results that we got. Here I'm showing you how many kids oriented fewer than 2 times. Orange is the population with autism, and in blue is the population that neurotypical kids. And what you can see is that the kids with autism are almost twice as likely to not orient to the name call. And so this is reproducing something that is known in the community. And this is the interesting part. So we reproduced something that was known in the community, but as we were doing that, we also, because we had a higher precision, we started to look at the time after the name call. And how much time did it take to the kids to orient? What we see in the blue is how many kids responded after 1 second, 2 seconds, and 3 seconds. And what you see is that the kids with the neurotypical kids tend to respond faster. And this was a new discovery. And so something that is it's cool about this example is that we can reproduce things that people already knew, but also we were able to discover new biomarkers. And we did that across these 4 different domains. So now we need to combine all these different things to come up with a single prediction. So we combined this to predict the likelihood of having autism, even these different biomarkers. And this is what we show and we can provide to the caregivers. So we have something that is explainable. We can show which are the particular features that are driving the score. So we can show that for this particular kid, the gaze pattern is looking like the autistic population, and we can show that for the different SHAP values, and across the different, we can show the background of how the autistic and the neurotypical distributions look like. So now the question, is this really working? Is this actually working to solve this problem? And the answer is, fortunately, yes. We show that we can achieve a sensitivity of over 80%, and we can achieve a specificity of over 90%. This is the true positive rate and the true negative rate. And so this is working, and we can actually use this to solve this problem. And if you want to see the details, we published this recently. The details are all in our Nature paper of 2023. And this is a big deal. The fact that this is working was actually highlighted by NIH in 2023 and one of the top 5 discoveries in health that year. So this is something that we're very proud of and is making a huge impact across the US, and we hope to make it also across the globe. So this is one example, and there is a lot more details on the reference that I put. But let me give you just a hint of the other research projects. So if you're working on similar things, we can talk over the coffee break. So this is the only slide that I'm going to use. So I know we're all craving to have a coffee, except the Uruguayans that have been surviving because they've been drinking mate this whole time. So I'm just going to, in this slide, finish my presentation. So these are the other projects that I'm involved, and I'm not having the time to give you details, but at least I want you to have the highlights so we can talk if you're interested. I work mostly on 3D and 2D data, so you can see these project clusters. My expertise is in computer vision, and I work with images and 3D point clouds. The works on the left, in particular, let me start with the top left. This is work that I'm doing with a company in the US called Restore 3D. This company has technology to print 3D personalized implants, so if you have problems, you have a car accident and you break bones, they can print things that are personalized to you. One of the challenges that we have is how we model this manifold of bones, how we model this 3-point cloud structure. And so we're working with them on that, and one interesting aspect is that these applications trigger novel technical questions. So we're in parallel to that work, we're working on how we do better deep learning tools to work on 3D data and understand the manifold with different shapes. I'm also working with improving neuronavigation tools for transcranial magnetic stimulation. TMS it's a technique where they send electromagnetic pulses to your brain. And one of the keys there is to be precise on where you're sending the pulses. So we're working using computer vision and 3D geometry to, 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 Another interesting project we're doing in Uruguay, this is work of a PhD student, Mercedes, is about improving neural navigation in agricultural environments. The key points and the scenes in agriculture are very challenging, and so we're trying to improve the way we can do robotics and SLAM in those conditions. This is work that we recently started collaborating with Rodrigo. Rodrigo Verchaes showed yesterday some work they're doing in cherries here in Chile, very interesting work, and we have similar data sets for apple crops. And there is a lot of work also that is being done in Argentina, so there is a lot of interesting work here in Latin America that we can leverage to improve that. I show you some of the work on behavioral phenotyping. We're doing this for phenotyping of autism. We're using that across other domains in psychiatry and psychology. So I can talk to you about those more in the coffee break. And we're working also, we have been working on the last 10 years on fraud detection with a Uruguayan company, UTE. One of the students is actually here at KHIPU as well, so I can connect you with Camilo, who work on this. And all of this is possible because I have the privilege to work with amazing collaborators. This work is done and supported by also great graduate students and postdocs, and the founding agencies and institutions that support this work. So I want to do a big thank to them and the families that allow us to collect data and do this research. And with that, I'm going to thank you all for your attention.
Thank you very much, Juan Matias. So we have a coffee break now. We are running a little bit late, so let's try to be back at 20 past 11. Yep.
here works.
No. Wait, let's wait. Let's wait 5 minutes.
Yeah. Don't judge me.
I'm definitely judging.
Oh, shoot. No, I lost it.
What's the Wikipedia article?
Hmm?
What's the Wikipedia article?
What's the Wikipedia page? It might. Can I make this full screen?
Let's click on the slideshow.
What?
Slideshow.
Yeah, I have the presenter notes. I was trying to, get that to work.
But I think for that you need to.
But it might be asking for too much.
Yeah, I think for that you need to.
Only,
I think now you're mirroring.
Yeah, let me just abort. I'm just gonna go mirror. Before I show everyone my screen. Okay. Okay. Seems like folks are. Can I have an hour still? Who? What? Oh, yes. I know Mate, but I could go with some high caffeine right now.
¿Cuándo le doy gas a esto? ¿Media?
Hello, hello.
Okay, we're gonna start the next session. Thank you. Thank you. So I'm gonna quickly introduce Luke, who is gonna give a talk that I'm very excited about. I heard a similar talk as this one, but not as polished a couple of years ago, and it was really, really good. So Luke is an AI researcher who's excited about bringing this technology into the world. In his free time, he plays with robotics, programming languages, electronics, 3D printing, and graphics. Luke was part of the initial team that built a low-key research preview that ended up becoming ChatGPT in OpenAI. Before that, he was a research scientist at Google Brain, and now he works in Thinking Machines Lab. In his words, exploring something new. A little known fact is that Luke and I met by chance almost 10 years ago in an Eclair dinner in Puerto Rico. Despite being in the same table with some very senior researchers and stuff, there were these 3 kids that I had no idea who they were, but apparently knew more machine learning than anyone else in the conference. And these 3 kids were Luke, Ishan Gulrajani, and Alec Radford, who ended up basically at different moments being kind of an integral part of ChatGPT and OpenAI. So yeah, he's been doing a lot of cool stuff ever since, and I'm excited to know more of what he's doing now.
Cool. Thank you so much, Martine, for that wonderful introduction, and thank you for having me here. So today I'm going to talk about large-scale reinforcement learning on language models. Sorry, stupid VS Code is going to drive me crazy. Okay. No. I think it was. Yeah, it is.
Hello.
Okay, but is that, do I have to be super close to it? Okay. Sweet. Great, so today I'm going to talk to you about large-scale reinforcement learning on language models. But first, a little bit about me. So previously, I was at OpenAI. I was part of the team creating ChatGPT. I was doing a mixture of sort of science, engineering, and also product work. It was sort of the full gamut of stuff there. But most recently, I'm one of the co-founders of Thinking Machine Labs. We're a new artificial intelligence research company focusing on the intersection of these large language model technologies and products. So I'm super excited to be here now. Cool. In this talk, I'm going to talk about basically what it takes to train, and in particular post-train, these large language model systems. I'm going to go over some background, what is post-training, some talk about various extensions and modifications to that general framework, a little bit about evaluation, a little bit about how and where product fits into all this, a little bit about compute and software systems to make this happen, and then end with a little bit of things more on the organizational side of things, of how you scale these large groups of researchers to build one model. First, what is post-training? So folks may have heard of pre-training. Post-training is the aptly named step after pre-training. It takes the model that was created there and sort of aligns it for various types of applications. Pre-training basically trains a model on the entire internet. You're trying to, the objective is to try to predict the next token on sort of large corpuses of data. It's extremely compute intensive and it requires tons and tons of data. It's, the way I like to think about it, it's sort of like a sponge. You try to shove as much information that you possibly can inside this one model, and that information is then there, and then the act of the rest of the processes are to try to extract that information. Post-training is the process to extract that information. So you take that sort of nice general model that you might have, and then you'll specialize it and sort of pull out various bits and pieces of things you might want it to do. So instead of trying to repeat the web pages as the pre-training objective, you're training it to behave in a certain way. So for example, it can be act like an assistant, can follow instructions, or things like that. These are often fairly specialized use cases, and oftentimes, at least in industry, they're used for powering some kind of products. So to give you a little bit of a flavor of the difference between these pre-trained models and these post-trained models, consider asking a model, give me a recipe for chili. The base model isn't very helpful. It first responds by saying, I don't have a recipe, and then it says it's complicated, and then it kind of rambles a bit, and then isn't very helpful. Whereas the post-trained model immediately does what you want it to do and gives you the recipe here. Yep. Okay, sorry, animations got weird. Cool, so systematically, post-training has two main pieces. First, we start with a pre-trained model, which takes in the whole internet. And then the first phase is supervised fine-tuning. Here we take demonstrations of the desired behavior we might want and fine-tune the pre-trained model to do those behaviors. After that step, we take the resulting model and apply RL on it. And this reinforcement learning tries to maximize some reward defined by, say, a preference model or, say, auto-checkable rewards. I'll get into a lot more detail on these rewards in the next couple slides. But first, let's briefly talk about supervised fine-tuning. This goes by a lot of names. It also goes by the term behavioral cloning. The core idea here is you want to take behaviors that are good, train the model to replicate those, and by doing that, the model will then act more like those behaviors and work in that way. So given a task, say follow some instructions, your job in this phase is to source some distributions of questions you want the model to perform well on, and then get demonstrations of that. One of the most common ways, and the easiest way, conceptually at least, is to leverage humans for this. So you can leverage human data or get human annotators to generate responses, sort of acting as if they're the language model. You can then take these demonstrations and fine-tune a model, given that prompt, to produce the answers that were then written by humans. The reinforcement learning part of this does not use demonstrations. So instead, you have given some kind of reward, and you use reinforcement learning to maximize this reward. Now, this is super general. There's lots of different types of rewards and things that you can try to optimize, but what's important is that you have to be able to check these things. So for example, did a program solve the competitive programming problem? Is fairly easy to check. If it passes unit tests, chances are it's right. Did it match the correct answer? This could be just like simple string matching. Does the answer have any spelling errors? Things like this. These don't define exactly how you want the model to behave. They define properties of how you want the model to behave that you then optimize. So if you have these two methods, the obvious question might be why use one and not the other. So for example, is if SFT, or why use SFT at all if you just want to use, or if RL is so great, why have demonstrations at all? So to answer this, consider trying to teach a model, or a human for that matter, to always respond to questions like a pirate. For every question, you have like a reward signal that's going to be some teacher saying good or bad. By default, if you ask a question to any pre-trained language model or any sane human, they're not going to act like a pirate. Every single response, the person's going to say, no, this is bad, no, 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 no. There's going to be no learning signal here, and you're going to be out of luck. Instead, it's a lot easier just to demonstrate with a couple demonstrations, oh, this is how you should act. And same goes for a language model. A couple demonstrations here or there will start to get the model to act like this, and then it will give the model a signal for then reinforcement learning. So the converse of this, if SFT is so great, why use RL at all? Empirically, RL seems to work much better. This has sort of been repeatedly found by a lot of labs. So that's, I think, the leading point here. Even with, though, like, and the other big factor here is to create demonstrations is hard. And even with, like, a lot of money and getting these high-quality demonstrations, especially at scale, is extremely challenging and gets increasingly more challenging the more complex the tasks you're trying to solve. The demonstrations are fundamentally bound by the demonstrators. And so as these models are doing more and more complicated tasks, it's like hard to source like experts in physics or experts in programming problems or things like that. Whereas RL, on the other hand, you sort of have this unbounded property. If you can define the objective, you can apply a lot of compute to it, and you can get better performance on that. So the general strategy that works pretty well is do a little bit of SFT to get a good policy, sort of fixes the exploration issues, and then use RL for the rest. And this sort of pattern and setup works surprisingly well. Okay, now to talk a little bit more about RL and sort of what types of optimization problems you're trying to solve. So the main objective you're trying to solve looks something like this. You have some optimization target. You have some distribution, my mouse is visible? Yeah, you have some distribution of prompts sampled from some data set of prompts. You then take your LLM policy pi, in this case, conditioned on that prompt, generate some results. So these are going to be like answers to your questions, for example. Then you have some reward function, which is a function of both the prompt and the generation. And you're trying to optimize this quantity. There's a lot of ways to do this. Before getting into one specific way, the two big themes, or the two big categories of RL algorithms, I would say, are online RL and offline RL. Online RL algorithms are things like policy gradients, reinforced, PPO, GRPO more recently. For offline RL, most recently for LLMs, there's DPO, but there's a whole host of other offline RL methods used for games. I would claim that online RL generally works better than offline RL. There's sort of a hand-wavy argument for this, which is it's a lot easier for the model to learn based off its mistakes. If you have a model that like learns, generates some output, and is bad, like that gets caught immediately by the reward and then fixed the next iteration. In addition to that, though, these online methods are also a lot more flexible. You can kind of put anything you want into that reward and optimize it, and with enough compute, that generally seems to work. There's one big con here, though, which is these online RL methods are often a lot more challenging to implement and work with. So this really only holds for if you want to train like state-of-the-art models or have a lot of compute or things like that. If you just want a model that like works well for some application, definitely consider offline methods because they're a lot simpler to implement, and they are definitely the 80-20 of complexity versus performance. Okay, so now to focus a little bit more on online RL, you have this objective above, and you want to be able to optimize it. So naturally, you want to take a gradient with respect to the parameters of your neural network here. The same trick gets used for the last 15 years. It goes by many different names. The log derivative trick, score function estimator, reinforced, policy gradients. It's all kind of the same thing. It all boils down to basically wanting to the gradient of the reward is the gradient of the log probability of the generation given the prompt multiplied by the reward. And there's a lot of symbols here, but intuitively all that's going on is you're sampling a bunch of completions and then grading them. The completions that work well, you're trying to increase the probability of them occurring. The ones that do badly, you're trying to decrease the probability of them. Now there's that last slide, sort of a pretty big oversimplification. There's a lot of tricks, I would say, to make this stuff work in practice. Things like reward normalization, for example. Gradient variance is often the name of the game here. You want to try to minimize the variance of your gradient. So things like value functions you can use. If you are doing slightly off policy online learning, there's various correction terms you might want to have. There's clipping, things like this. This is where PPO and methods like that come in. I'm not going to get into any of the tricks because I think the general principle of having like the simplest algorithm you possibly can often works really well here. And that simple algorithm with a lot of compute usually leads to the best results. So you might need one of these tricks if something goes unstable or something breaks, but in general, striving for the simplest thing with a lot of compute is sort of always the way to go. Okay, so now with the basics of post-training RL out of the way, let's talk a little bit about extensions and modifications. So what I just described in the previous slide is extremely general. You can apply a lot of different types of learning problems in here. So for example, chain of thought or reasoning models kind of fits naturally here. RL from human feedback, tool use, things like this. In a lot of these industrial models, they might take in images, they might take in audio, they might output audio, they might be multi-turn, things like that. All these methods you can kind of fit pretty naturally in the RL framework and then use optimization to improve performance on them. In this talk, I'm going to talk only about the first 3, though, just mostly based on time. So for chain of thought models, the idea here is to teach a model to think. And by giving it time to think and space to think, the idea is it's going to perform better. So this is particularly applicable for like math problems, where it might think through multiple steps and then give you the final result, and that's a lot easier than jumping to the final result. To actually make this happen, it's not too difficult. The first step is you need to have some demonstrations to tell it to think. So these are going to be basically getting the model into the right initial starting point for RL, where it starts to use some of these tokens. And then RL on some objective. And then all you have to do from there is apply RL on that model. There's one slight trick here, which is you want to be grading the result of the thinking, not the thinking itself. This sort of makes sense, especially if you're thinking about like math. You want to like check only the final answer and not like the process that could be inscrutable along the way. One cool thing about these models and this sort of type of setup is over the course of optimization, the model actually learns that thinking it's useful. And as a result, thanks to optimization from RL, it thinks more. And so to get the best results, you want to use a really long context, because eventually the model will keep using tokens to think and keep getting better and better and better. And with that long context, like lots and lots of compute also helps quite a lot. So in the SFT phase, I briefly mentioned this last slide, but like bootstrapping this thinking procedure is like fairly important, because this is harder to have emerge naturally from scratch. So you can see here, this is a figure from the DeepSeek paper, with the x-axis being training iterations, so number of steps you take in RL, and the y-axis being the average length per response. And over the course of RL, like the completion lengths are only growing, and as a result, the accuracy often only grows as well. For those keen observers, the last figure was actually not using SFT. It was actually using a prompted model. But it's the same general principle. So SFT is not the only way to get the model to have this kind of like initial behavior. Another method that the DeepSeek folks did is prompting it. But it's the same idea. It gets the model into this initial area where it can start to think a little bit, and then RL takes the rest. So in this case, in the DeepSeek paper, they used a prompt that looks something like this. It basically just says, think about stuff before answering, and that's also enough to start to evoke this behavior. Yeah, so exploration's hard. You can do things from scratch, but in general, it's like, why make your life hard? Just get some number of examples from human demonstrations and use those. It'll save you many headaches from having to solve the actually hard problem of exploration. I think a great example of this is actually buried in the AlphaStar paper. They did a series of ablations, including one on human data usage. And if you just take out the human data, you do really, really poorly on this task. And this is like by far the worst ablation out of all their ablations, which is kind of funny. So even here, like on a totally different setting, like just a little bit of human demonstration, or this human demonstration really helps a lot, even when RL plays a big impact. Okay. Next up, I want to talk about RL from human feedback, or RLHF. So the core idea here and sort of the extension of the initial RL setup is, how do you grade like more fuzzy answers? Like, how do you grade things that you can't necessarily say, is this correct or is this not correct? So for example, you might have a prompt that's like, write me an essay on the history of sandwiches. How do you know if that's good or not? It's hard. There's no like Python program you can write down that'll like do that. And the solution that the RLHF literature has figured out is you can use reward models. So you train a model to act as this reward and then do RL on that model. One common way to train these models is you can collect comparisons. So given a model and a prompt, you can generate 2 or more generations and then give these generations to humans and say which one's better, which one's worse. This will give you a data set of these sort of comparisons. You can train a model to then act like a human here. So it's going to predict what a human would say. And then you can use that model at reinforcement learning time. The quality of this reward model ends up mattering quite a lot. Making that model more accurate, though, is also like not particularly hard, I would say. The same tricks of reinforcement learning, or sorry, the same tricks of machine learning still apply here. So more data definitely helps. You can use a strong base model or a large base model to fine-tune your reward model off of, and that also helps a great deal. Anthropic did a little bit more of like a careful study here, just to give kind of the flavor of this. On the, so this plot here on the x-axis is training comparisons, so amount of data. Y-axis is accuracy, or sort of how good your reward model is. And in color, you have parameter count. And sure enough, more data, larger model, you get better and better performance. And these things sort of trade off. So if you don't have as much data and have a bigger model, you can do that. Another less obvious way to get the reward models to be stronger is to give them more information. So for example, if you want a reward model to grade questions, consider also giving the reward model the correct answer, or like details of the correct answer. So maybe in your essay about sandwiches, you wanted to mention like BLTs. Like say that to the reward model, and then the reward model, like put that in the reward model's prompt, and then the reward model will do a better job at picking out some details like this. There's a whole host of ways you can improve these, though, that I'm not going to touch upon, but sort of the sky's the limit here. There's a lot of stuff you can do. Once you have this reward model and are trying to optimize against it, there are also some other issues that spring up. So in general, these reward models are trained on a very particular distribution of data. In particular, they're trained on comparisons sampled from some of your prior models. And now, if you move further away from that, so for example, if all your comparisons are in English, and then suddenly your model starts speaking in Chinese, your reward model is very out of distribution, and it's not going to do as good of a job grading the results. And this can lead to sort of over-optimization and sort of an interesting type of overfitting. The solution that early RLHF work did is basically to add a regularizer to stay close to the initialization, so stay close to the initial policy that you collected data from. The metric in question people often use is the KL divergence between the two, and people then look at the reward model score versus this KL divergence. So this is also a figure from Anthropic, but you can see this KL reward frontier in the bottom right. So x-axis is this KL divergence, the square root of it, I guess, and then the y-axis is the reward. And you can see the reward both on a training preference model, so this is used during training, and a test preference model. And what's cool here is as you train more and more and more, your model you're training gets further away as measured by KL, and then you can actually start to see a little bit of overfitting because you're over-optimizing the training reward, and it's not generalizing to the test reward. One thing that people do a lot to fix this kind of issue is just to make it iterative. So if you have a model, you want to optimize it to do better and better on a certain reward model, you're going to over-optimize, you're going to start exploiting certain areas of this reward model. So instead of like going crazy trying to like regularize and so on, you can just do the whole procedure again. You can generate more completions, you can give those to humans, you can get them scored, you can train another reward model, and then re-optimize. And doing this over and over and over again improves performance pretty assuredly. Okay, the last of the extensions that I wanted to briefly chat about is tool use. The idea here is you can teach the model to produce tokens that are then interpreted as things that you should run code against, essentially. So as an example, this is what a high-level sketch of what it could look like for like a calculator tool. The user might put in some prompt that's like, what is 20 plus 22? The model now is going to produce some kind of syntax, basically, that tells whatever is running it, hey, this is a tool call. In this case, it's just putting it in triangle brackets and putting some math in the middle. The Python code or whatever code outside of that's then going to see that. It's going to run that in this case, a calculator. And then it's going to put these resulting tokens inside the prompt and then pass the mic back to the language model. And then the language model is going to continue off, being able to see this because it's now in its context and be able to respond, yes, the answer is 42. There's a million ways to set up the exact tokenization and how exactly you parse things and so on, but this is the core idea. And what's cool is you just have to do the same thing again. You need some initial SFTX for exploration. Same idea. Without some kind of demonstrations, the model will have no idea that these tools exist and that they can call it. So you need to initially show the model this. This can be via human data or it could be via prompts. And then during RL time, if you have that tool on, so you do the same procedure that I just showed you, but now during the RL loops, the tool will get more usage if the tool is like helpful for your goal, or less useful if it's not helpful for your goal. So you get that all kind of for free because you're applying optimization to it, essentially. So with all these things and all these methods, I've mentioned data a lot. Data really is one of the most important things in all this space. Generating high quality data and making sure it does what you want it to do is by far the leading thing to improving performance on these models. I think one interesting thing is a lot of earlier academic benchmarks often focus on testing algorithms on a fixed data set. So like ImageNet, MNIST, CFAR, Atari even, like all these sort of fit that bill. But a lot of the post-training work and a lot of the work people are doing, especially in more industrial settings, is iterating on the data itself and then caring a lot less about the algorithms. Like there's going to be some RL optimization objective that like works, and then you just cycle through data sets or try to improve quality of data sets. There's different kinds of data sets now, so you kind of have to think how you want to spend your effort on each of these. There's demonstrations, as I mentioned earlier. There's comparisons if you're training reward models, things like that. And there's also this kind of new kind, which is like prompts and the ability to grade them. So if you have any kind of question that you can grade, you can now do RL against it. And so generating those tuples essentially are another area that you can sort of add data to these systems. Cool. Next up, I wanted to briefly touch upon some evaluation stuff. So language model evaluation has really kind of, I would say, exploded. There's huge piles of evals that test all sorts of different things in a variety of generality. I see them as there's sort of a few themes of them. There's like the more traditional benchmarks. I wasn't sure quite what to call these, but these are like programmatically checkable things. So for example, multiple choice question answer. This is stuff like MMLU, for example, falls under this. Short answer type things, so like what's the capital of France? Did it answer Paris? Yes. If not, no. As well as perplexity. These all still work, still great. They're a little restrictive in sort of the types of things that you can evaluate. Given that people have been exploring some other methods to evaluate these things, one pretty prevalent one is this LLM as judge, or sort of this fuzzy match idea. The core idea here is you ask LLMs to grade the answers. And similar with reward models, you can give the prompted thing the correct answer, and it'll have a lot easier time to grade the thing. Pros here, a lot more flexible. Cons here, everything starts to become fuzzier, essentially. It's much harder to determine correctness. There's much more moving pieces, and you don't have that like rock solid guarantee of, oh, my model scored X on this data set, it must be perfect. You kind of have to be more in the weeds because the model could be tricking the grader, let's say, or something like that could be happening. These type of evaluations can be done in sort of two ways. You can operate on a single answer. So for example, like, did the answer mention Paris if the question is what's the capital of France? Or it could be pairwise, similar to how you collect human evals. So you could give 2 generations and say, okay, which one of these 2 is better? And then finally, the last main big category of eval is human evals. Much like LLM as judge, you instead replace it with a human. So often these are, you take 2 generations and then have humans compare the 2. And there's a bunch of different systems right now that are set up like this. Like LLMsys, for example, is sort of the most popular one at the moment, I would say. Scale has a bunch of stuff here. And then a lot of companies have their own internal in-house evaluation here, but it's all kind of the same idea. You might change prompts. You might change the pool of people you're using to look at these answers, but it's all kind of the same idea. The last one, which I think is sort of unique to is unique to when you have a product, is actually using the product itself. Often your goal is to train a model that people want to use or like, and so you can leverage the product itself as a way to get a signal on that. The most obvious is qualitative metrics with A/B tests. So you can take a fraction of your traffic, send it to certain subsets of people, and then measure things like time on the app, thumbs up rate, number of back and forths to and fro. Actually picking these metrics that you're doing your A/B test is extremely hard and has ramifications in what you pick. I don't think there's any one correct answer here, but monitoring many of them is definitely better than sort of hyper-focusing on, say, time in app, which will lead to some negatives, I'll say. In addition to sort of the more qualitative stuff, there's also a lot of quantitative stuff you can do. User studies, for example, talking to people, trying to understand what they like, what they don't like. This sort of thing will then inform essentially how you edit the data, what types of data you need, what types of areas you're weak on, and then you can go from there. So I see these sort of on a spectrum. If your use case is focusing on products, the most representative are these product metrics, but these are also kind of the slowest. These take order weeks to get signal on often, and that comes down to the fact that they're super noisy. Like measuring thumbs up, thumbs down, you need quite a lot of samples to get enough statistical significance to draw conclusions from that. Going in the less representative direction, human evals, these are much faster. They give you a quick demonstration. They're faster because you can pay humans to do these tasks. And they're faster also because you have control over the prompt distribution. So you can, for example, find only hard prompts to give to humans, and that'll sort of also boost your statistical significance. And finally, on the least representative, but really convenient, because they take hours to run, are the more standard benchmarks, including LLM as judge type stuff. So whenever I talk about evals, I always kind of step back and think but what's the point? What are we actually trying to do here? People often fight on these benchmarks all over the place, being my model's better than your model, this sort of thing, but not over here, and so on. We're doing all this work to presumably solve some kind of problem, and we should be explicit about what that problem is, and then try to think through our evals to see if they are representative of that, or actually tell us something there, instead of just blindly trying to work for it. So if you know what that problem is, if you know the distribution of tasks you want your model to perform well on, you can just test on that, and it's fine. And have faith that your evals are going to be predictive of the performance that you care about. Now, things get tricky when you don't know what this is. And I would argue a lot of the frontier research labs and so on are always trying to pursue this generality without knowing exactly the types of distribution of problems they care about. And in this case, it gets much harder. I would say you really have to consider a wide variety of evals in this case, because any one eval is sort of it's easy to overfit on. You might not just care about competitive programming, for example. But when you have a lot of evals, working with that large number of evals is also quite challenging. There's multiple ways to aggregate numbers and compare models, for example. Like simple averages are one way. You can just add up the eval metrics on all your evals you have and take a mean and say if it's higher on that, you're better. But maybe that's not actually what you want. Maybe you want to care something closer to worst case, for example. Like maybe you really care if your model is really bad at instruction following but really good at competitive programming. Maybe that will like feel like it's less general in that sense. Stepping even further back, like what we're kind of trying to do here is optimize unspecified goals. I think this is very related to what all the alignment work is essentially. It's when your goal itself is really hard to write down and you want to nevertheless do better on it. And it's going to be a hard problem no matter what because of all that uncertainty. I think one other interesting property of language model evals is we're entering an era where people can basically juice the numbers or artificially or sort of target particular evals and make them much, much better, kind of at the expense of a lot of other stuff. I think this is partially how the sort of game of these benchmarks have emerged. So in more traditional ML settings, as I mentioned earlier, you define a data set, there's a train set, there's a test set, you train a model on the train set, and then you test on the test set. It's very clean, it's very well defined, and as a result has held up for quite a long time. Pre-training changes this a little bit. You define evals now, things you want to do well on, but you're training still on something that's approximately the same data set. Most of these large models train on like as much of the internet as they can get, and that's super general by definition. And so that generality is sort of carrying you forward. Like if you define your evals, like MMLU for example, that'll probably be predictive on programming just because the internet is super general and assuming you're not like hyper-focusing on selecting only programming tasks. Post-training, everything's a little different. You define an eval, but now oftentimes people collect data to target problem areas very related to that eval. So for example, competitive programming. Whole bunches of groups are now sort of fighting over these AMI benchmarks, for example. And the name of the game and sort of the way to optimize that, I mean, it's sort of ML 101. You get data as close as you possibly can to the competitive programming benchmark that you want to do well on without cheating. So like maybe this is past year's AMIs. Maybe this is like you pay people to write AMI-related questions. Like, I don't know. But this feels kind of like wrong. Everyone's sort of marching towards this same eval and sort of getting arbitrarily close to the point where you're actually cheating. I think the big point here is in these post-trained models, you've started to exchange generality with the specificity, and that's sort of what's causing all this to fall apart. Some other examples of this that came up recently on Twitter, the ARC problem, for example. There's a question of, can you train on the ARC training set and then test on the ARC test set? Is that considered okay? This caused some heated debate. Some people said yes, some people said no. I don't think there's an actual answer to that. Another one that people I've heard of talk of doing is training on LLMs prompts. If everyone cares so much about LLMs, you can just take the prompts and train on them. The way LLMs is set up is that's not cheating because they're generating different prompts to test the models, but it's going to come from the same distribution. And by sort of juicing that area or collecting more and more prompts from that particular area, you'll do better on it. Cool. I'm going to take a drink of water. Okay. So switching gears a little bit, I want to talk a little bit about products and how they kind of fit in here. I think products in AI have sort of really interesting spot. There's sort of the obvious thing, which is running these big AI models and so on costs a lot of money and products make money. This is, I think, the least interesting point, but for some places is sort of like an inevitable and sort of a required factor of them. I think what's more interesting is sort of how they can give back to the research itself. So I think one less obvious area is on evaluations. As I mentioned earlier, these products, in some sense, are the ultimate eval. If you really care about having your model get out there and improve people's lives, what better way to do that and to test that than to measure it on something people are actually using? I think it also gets at some alignment type problems. It's hard to write down exactly what people will want in this case, but you can kind of measure it a little bit. So playing that game of trying to figure out what exactly are you trying to optimize, having this product there to explore and to try things out in the real world helps a lot with that. Another less obvious area is they give you feedback loops. And this can come in a wide variety of different areas. By getting the model out there, you get this sort of red team type effect. You have people trying it, you can understand issues, you can understand benefits. There's like direct ways to do this. Like a bunch of these apps have thumbs up, thumbs down. There's like pairwise comparisons in a bunch of them. But there's also like indirect ways, finding things that frustrate users. Like you can either do this programmatically, for example, by looking at transcripts, things like that, or you can just like get the pulse of people using the product. And you can quickly discover blind spots of the model or areas that you should improve that are sort of outside the domain that most of academia covers in terms of evals. I would say the last thing that's less obvious is you get grounding. ML research in general likes a super clean benchmark. When you have it, like people like nothing more than to like hammer at hammer at the number to make it go up. Like I got into ML via Kaggle. Like it's so much fun. It's so addictive to have the number go up. But you lose connection to sort of what the goals are to begin with. Like there's a lot of focus on competitive programming and hard math right now, for example. But most people who want to use these models might not care if it can solve unsolved math problems. They might care about other things, like how is its writing quality, things like this. And by sort of forcing yourself to have your model out there and so on, like you can start to confront this and you sort of check your, well, working on competitive programming helps because it makes the model smarter. Well, does it really help a lot of the use cases you're caring about? Okay, compute and software systems. Switching gears entirely, because I think this is important but often not talked about here. So the first thing I'll say is compute like really matters. And data center infrastructure and technology to kind of make this up has powered like all of the frontier AI models to like an extreme extent. This stuff's like kind of crazy. Like the analogy that I could go into a bunch of different axes of this, but the one I wanted to focus on is just power. Even finding power and sourcing power is like hard. This is actually one of the slowest things in building data centers. It's figuring out where you can get your power from. You can't just plug these things into the grid. The grid can't take it. So the XAI cluster that you might have seen the news about is 100,000 H100s. By semi-analysis, I believe, they estimated the power usage is something like 150 megawatts. To put this in context, all of Chile is about 36,000. The single largest power plant in Chile is 780 megawatts. This, I think, is a coal plant. And this one data center, if you just do the math out, is between 1% and 5% of all of Santiago's energy usage. And this is one company's data center and only one of them. So it's really an insane amount of power. And this stuff costs a fortune too. I mean, 100,000 H100s was like $3 to $4 billion of dollars. And it's already obsolete as of around now, thanks to the fact that the new NVIDIA chip just is like coming online now. So while ridiculous compute is often needed to create these SOTA models, I put often there because I think there's varying degrees of waste. I would say within an order of magnitude or two is needed, not necessarily the 100,000 accelerator amount. But I would say ridiculous compute's not needed to solve a lot of really hard problems in this space. I think one really compelling and promising sort of mindset that came out of OpenAI early on that sort of powered a lot of the GPT series, in particular GPT-4, this is from the GPT-4 blog, or paper, I forget which, is this notion of scaling laws. The idea here is you can run smaller scale experiments and look at how the differences in performance change, or how things change as a function of scale, and then extrapolate. So in this case, GPT-4 is here. This has a compute unit of 1. Each tick is 100x. So you can run experiments that are 2, 4, 6 orders of magnitude smaller compute and still have some sort of predictability on the final result. And this sort of fact lets people do a lot of research on smaller scale and then have faith that when you combine everything together, you get a good result. people do this. I wanted to highlight some work that's going on, mostly on Twitter actually, which is this like nano GPT thing. So for those not familiar, Andrej Karpathy made a little GPT-2 reproduction, put it on the internet, and then some point people started like hammering at it, just making it faster and faster and faster and faster and faster with various different improvements. But what's cool here is then someone ran it on the larger scale. So he had two scales. He had a smaller model and a larger model. And then he ran it on the larger scale model and just grabbed all the good stuff, shoved it in, and sure enough, it led to like a 8 to 10x improvement in wall clock time. So this is not the most scientific in that there's no like exact predictability, but the same idea holds. You can do a lot of great stuff on small scale, track how it changes on large scale, and then get improvements. Now post-training, all that was pre-training. Post-training doesn't have anything like this. And I think this is like a big open problem and sort of something that's slowing down a lot of the research because a lot of people sort of rush to the largest scale model and so on. But there isn't this like notion of like what types of things can we do on small scale? How can we measure the predictability of that? How can we see how that impacts final model performance or what changes at scale or how things change at scale? Okay, so back to compute. Another big open question on all this stuff is, so you have all this compute, how do you actually allocate it? So in the early days, you had pre-training and that was easy. Just pour it all on the pre-training and you're good to go. Whereas now there's sort of a couple other axes that have been emerging. There's post-training or RL, that also takes compute, traditionally much, much less than pre-training. And there's also test time compute. And all these things sort of trade off compute, and sort of you might want to figure out the optimal layout, and I don't think anyone knows the answer to that right now. There have been some cool results, though. Again, this is buried in an appendix of Keeming, Keeming 1.5. It's a model from Moonshot.ai, looking at some of this. So here is a bunch of different benchmarks. On the x-axis, it's response length. So the x-axis can be thought of like as test time scaling. And then in color, you have different model sizes. So orange is a big model, blue is a small model. That can be thought of as like pre-training size or like model size scaling. And what's cool here is you get a different slope. For 3 of the 4 benchmarks tested, the slope of improvement given more additional test time compute actually is improving as a function of number of tokens used. This is obviously like quite preliminary, it was in their appendix, but I'm excited to see where sort of understanding how these trade-offs work, essentially, goes in the future. Okay, even further afield from a traditional academic conference, I would say the software systems matter a ton here. If you're spending all this amount of money on compute, you really need to make sure everything's screaming fast as measured by how much you're utilizing the hardware. I think another interesting factor of post-training is the systems requirements change a great deal. Pre-training is all about this one giant synchronous workflow, basically lockstep doing gradient steps. Whereas post-training, there's like lots of different things going on. You might want to train, you might have some stuff training, you might have some stuff sampling, you have some stuff doing reward calculations. It's much more dynamic. People often make it not synchronous as well. I'm not going to get into really much of the details on how to train these things. I would definitely recommend this great book here from Google if folks are interested in really understanding sort of all the intricacies of this stuff. The one thing I did want to talk about is sort of the rough layout of how these RL jobs are set up as compared to sort of pre-training jobs. In general, you have groups of machines that are responsible for subsets of stuff. So in this particular case, you have a set of workers used for training. This will like have the transformer weights, it'll do gradient updates, and looks closer to what pre-training jobs might be. You have these rollout workers. This is a set of machines that take weights from the trainer and sample from the model. These samples then go to a replay buffer or some controller and get graded by some other set of machines, which are going to be running various rewards. And then these get batched and sent to the trainer, and then that whole loop kind of continues. The one big thing that is different from online RL versus pre-training is inference. You now have to put inference as part of your training procedure. And it's different than most of the normal goals from inference. Like normally if you talk about inference, it's like, oh, this is going to like power some product, therefore I care about it being super low latency because users don't want to wait. For RL, it's actually the reverse. You want to get the best out of your hardware, so you want to make sure you have as high throughput as you possibly can. And this changes a lot of the design decisions that you would do, and sort of leads to different sort of resulting architectural systems than you might find in, say, VLM or SGLang, for example. The TLDR, like the leading thing, is just make your batch size as big as you possibly can, and then do things to make the batch size bigger. But to give you sort of a sense of these trade-off, one way I like to think about it is you can plot figures something like the bottom right, which is on the x-axis you have the latency per token generated, and on the y-axis you have something proportional to throughput. In this case, it's cost, because if it's cheap, you can run more of them essentially. So you can think of it essentially as throughput. And then different configurations now on like a system side of things. So for example, different batch sizes or different number of parallelism for sharding your tensors will give you different points on this curve. The one thing I wanted to highlight though is that the delta between the cheapest and lowest latency is pretty big. It's like a factor of 8 to 10, which is totally worth doing and totally worth considering. Because a factor of 8 in your total compute when you're spending this much is a lot. Another big trick that people do is asynchronous RL. This is something that DeepMind, I would say, pioneered a few years back. Huge numbers of really great papers out of them, basically showing that you can do large-scale reinforcement learning without having things be synchronous. Same idea applies for language models. You often want to do some kind of asynchronicity to make the best use of your sampling and your training machines, basically, so that you can have everything humming all at the same time. I have a screenshot here that basically is demonstrating like a one-step lagged version. So you can imagine sampling from like time step t-1 and then using that to train time step t+1, if I did that right. But the idea is you're training on slightly stale data. It's not so stale that it'll cause problems. There's various RL tricks you can do to correct for that. But in exchange for these, a little bit of off-policiness, you get a lot higher utilization. Okay. Finally, in the remaining 10 minutes, I want to talk a little bit about organizational complexity and sort of how all these pieces fit together. So the model complexity continues to grow. These models can do so many things, and especially at OpenAI, sort of seeing all this, all the complexity add up really caused a lot of changes to how we had to do research and work. So just in my time at OpenAI, the post-training team was working with multiple sized models. There was like 4 of them. We added tools. There was like browsing. There was like a retrieval tool. There was like a code interpreter tool. There was like this ability to put memory on the side. There was like free-form function execution with plugins. Various things for safety, like following policies online. Like if you need to switch model behavior sort of on the fly, you can do that. Lots of stuff on refusal boundaries. Mid-training, we wanted to add in making the model fresher, for example. New architectures themselves. There's multimodal. Like over my time there, these things took in images. They output audio. Like the list goes on. Like human data. It got like crazy. And to make up for this, like our team ended up growing from like 5-ish to like 200, or sorry, to like 100-ish, a little more than 100 people. Just to kind of manage all this. And then that caused its own problems, because now you have 200 people or 100 people all trying to collaborate on basically this one artifact. And by the end there, it really kind of felt like this. People are just like lobbing things over, and like you try to get it all into a reasonable spot so that nothing catastrophic happens. But I think we're definitely in the early days of trying to figure out how to manage all this complexity. One sort of thing we ended up doing that I would say is not rocket science is figuring out a procedure that subteams can sort of improve various parts of the model and then integrate it back into one model at the end of the day. We called this the mainline model. The TLDR is we figured out a setup to de-risk using less compute. So this could be a smaller model size, it could be subsets of data, it could be, there's sort of a lot of ways you might want to do this. And then some set of evals that basically like shouldn't regress, or some kind of like, hey, is the thing you said you're doing actually doing it? Like if you are editing browsing, you should improve browsing and you should be able to like see that. And then if you sort of pass those tests essentially, so you have like a little packet, if you like pass those tests, we then integrate it into one big model, and that sort of kicks off periodically. We train the thing and basically cross your fingers because there's so many things that are new, and you have to do that because you can't afford to train, like you can't afford to do like the careful science in this point. You can't afford to train the big model or replicates of the big model on each individual ablation just because you run out of time and money. When things go wrong, as they inevitably do, we had to have some kind of procedure to essentially roll back. Like you can imagine rolling back or starting to bisect or things like this. But in practice, this stuff got messy very quickly. Yeah, so I would say partial success. I mean, it clearly worked. We were able to get some models out. But things still break quite a lot at scale. And by that I mean like something that works on small scale, for example, something that shows promise in the de-risk setting, might just have some catastrophic thing that happens on the larger scale that we would not have been able to predict and wouldn't know how to predict, just kind of showed up. Interactions between interventions is particularly scary. This comes up a lot for things like boundaries between things, like refusals, for example. Like if you imagine you have a data set that tries to increase instruction following, and you have a data set that tries to not follow all the instructions, those are kind of at odds. So balancing that and sort of working with things like that, and there's a lot of other places where they can sort of bash heads. I think one big thing comes back to evals. When you have a really long, when you don't have sort of smaller scale evals that are perfectly predictive, because as I was saying earlier, that's like an incredibly hard problem to have, small scale evals that are like perfectly predictive of everything, you need to get the signal you trust the most, which in our case was often product metrics. And when that takes time, you have to train the model and then wait a while for like A/B tests to give statistical significance, you have a really long time delay. So if your problem itself you don't spot until down the line, like you're talking months to fix this stuff now, because it takes like some period of time to train, some period of time to eval. You have to figure out what happened. That takes somebody some time. Fix the thing, do the whole de-risk procedure, get this model in there, re-put it in the A/B tests, and like that's just one shot. And with some of these things, we don't get it right the first shot. It takes a few shots. There's also a whole host of other things that just go wrong. The amount of like bugs and things like that on like just simple software, like configuration bugs or like bugs in the training code, like someone updated some kernel somewhere and it changed the numerics in some way that broke something, definitely happen and sort of add more FUD to this whole procedure. Because now like it's like, oh, did this break because of this? Did this break because of this? Unclear. You kind of have to sort of have all that in your head and all that to focus on. Cool. So yeah, hopefully this was useful. I went, as a quick summary, talking a little bit, I talked a little bit about sort of what post-training is. So both the SFT from demonstrations piece and then the reinforcement learning and sort of how that fits. I talked about how there are various extensions that kind of fit in this framework. Things like chain of thought, for example, things like tool use, things like RLHF, or learning from reward models. Briefly touched upon evaluations, product, software, which again, to reiterate, is sort of like this is like the core thing of a lot of this technology, and sort of really maxing that out and treating it as like a first-class citizen is extremely important. And then finally, sort of how all this stuff comes together as a company trying to train models. To end, I would say that I think managing complexity is sort of a really big thing that basically needs to be figured out by the field. Abstractions are a great technology or a great idea, I don't know what they are, that have helped software quite a lot, and sort of building good abstractions like really propels a community or people like forward in time because it lets people put less in their head. But sadly with ML, there aren't that great abstractions. Like things break down. Like I was just talking with somebody earlier today about like numbers, right? Like floating points, numbers, are no longer numbers. Like people are trained in lower precision, and then you have to think, well, what does multiplication actually mean anymore? So having to think keep all this in the stack all this in your head is sort of sadly a requirement now, but I don't think it's like a necessary, like I don't think this is the way it should go. I think people should start to figure out sort of more and more abstractions for things like this. So with that, thank you all. Please check out our new website, thinkingmachines.ai, and thanks so much. Happy to take any questions if I have time.
Thank you so much. We have time for 2 questions. I think, yeah, you were first. Let's go.
Thank you. I wanted to ask about reinforcement learning to generate chain of thought. Is there any way to measure the correctness not just of the final answer, but of the chain of thought itself, of the reasoning process?
Yeah, so you could definitely try to do things like that. There have been a couple of papers that are of the same spirit. Like there was like a process supervision paper from OpenAI before all this chain of thought stuff became super popular that did some stuff like this. So like it does work, but it comes with like other kinds of trade-offs that I won't be able to speak to super well. DeepSeek also does this for safety. I forget. There's a detail in the DeepSeek R1 paper if you're curious.
Okay, one more question.
Hey, so I will go against that direction. I saw some researchers that are proposing to don't use language tokens and make the LLM to think in a free space. I mean, we understand the alignment problem there, but I want to know your take on this in the general approach, and more specifically, if you think that will just make this process more efficient, or will unblock the LLM to access some behavior that it's not possible with the discrete space.
Yeah, I'm super excited about those methods. I've not seen any ones that have like really like, okay, this is the next thing, this blows it out of the park, but there's been a number of attempts that I have seen. They're all published papers now. My guess is you would get shorter chain of thoughts, which is actually a massive win because like compute is so expensive. If you save a factor of 2 on tokens, you've like saved a factor of 2 on your compute, and that's worth quite a lot. So I'm definitely excited to see where those go.
Thank you.
Okay, maybe thank Luke one more time. And I have a small announcement. The reimbursement for the travel is going to be at 1 p.m. in the front desk. And that's it. Let's go have lunch.
Thanks, everyone.
Ya lo vi, boludo. Estaba al lado tuyo, boludo. No me prestás atención, boludo.
Bueno, bien, entonces ya está todo resuelto.
¿Cuándo llegaste?
Llegué ayer.
Ah, ¿y qué tal?
Bien, bien, tranqui.
Sí, sí, sí. Voy a necesitar los dos.
Disculpa, ¿me dejas conectar la computadora?
¿Mandé?
Espera, aguantá, te voy a introducir y todo.
Sí, no, pero voy a...
Te voy a contar sobre Ámsterdam, boludo.
Sobre cuando nos conocimos, es la que no.
No, tranqui. Hay unas cuantas que tengo que omitir,
Ah.
Guys, we are about to begin. So, come in, settle down, take your seats. Dale, boludo.
Hola, hola. Para usar el clicker, ¿se puede o no? No.
No está más. Se lo hicieron.
A ver, déjame.
Ah, pará, Andrés. No. Ah, sí, pará. Andrés, probá ahora. Pero probá ahora, boludo. Dale. ¿Qué hice? Andrés, probá, ya lo conecté. Ya está, lo perdí.
Bueno, si no me importa, solo era para poderme cambiar.
Okay, let's begin the next talk. I won't tell the story of how Andres and I met. For that, you'll have to catch him off guard. But instead, I will say some nice things. So Andres does research on autonomous goal formation, reasoning, and consciousness in AI. Currently, or up until last year, as a research affiliate at the Montreal Institute for Learning Algorithms. He has a PhD from Brain and Cognitive Sciences from MIT, was the founder and CEO of state-of-the-art.ai. He co-founded an AI conference in Latin America called RIA, very similar to KHIPU. He worked in Facebook AI research, represents Mexico in the International Mathematical Olympiad, and has written several research papers and one book. He enjoys playing soccer, snowboarding, and backpacking. And a little known fact is that for the last year he was working in Mila with Yoshua Bengio, trying to understand consciousness, but before, he took a year and a half to work as a professional poker player, doing extremely well in the World Series of Poker. So yeah, that's also something to talk to him about.
Not that extremely well, but
he was in the news several times. I leave it up to you. Okay, without further ado, this is Andres.
Okay. Thank you. So I'm really excited to be here for two reasons. One is because this talk is really interesting to me, especially with everything that's happening in AI right now. Things are moving so fast, and this is becoming very relevant. Also, because it's a special privilege to be in KHIPU with my friends. I organized a conference in Mexico with other people that are also here, called RIA. And KHIPU and RIA are like conferencias hermanas. So it's just a special place to be, and I'm very happy and thankful to be able to present here. And I will talk about minds and whether we are building minds. And that can get very hand-wavy, so I'll try to be grounded, and I'll talk about three things in particular. Things around thinking, things around preferences, and things around experiencing. And it is the case that, like in 2015, when I started in AI, people would say, oh, deep learning is impressive, but it's far from like human capabilities. Then with language, when large language models came about in 2020, it was like, no, actually, they are great at language, but they are still lacking a lot of things. Now it's really starting to look like they do behave and have much more agency and autonomy and things like that. And it's also improving quickly, right? So let's go at these three parts. Let me keep track of my time here. Okay. So let's start with theory of mind, which is a concept from cognitive science, which is the capability of systems, brains and minds, to represent states of others. Do they have intentions? Do they have beliefs? Do they have desires? And a classical experiment used to test theory of mind in kids is this Sally-Ann experiment where there's a protagonist, Sally, which puts an object somewhere, and then there's another character which moves that object from place, but the protagonist does not see it. And then you ask the subject, the kid or the person being tested, like, what does Sally believe? Is the object where she left it, or is the object where she's not seeing it? Now, the kid saw that it was moved, so at a certain age, they do not infer that the protagonist cannot make that inference and just say, well, they believe it's where it is. But at a certain point, they start developing the capability of inferring, oh, but she doesn't have that belief. And this is something that all animals, even great apes, trail far behind from humans in tasks that have to do with theory of mind. So what about theory of mind in LLMs? Well, one way of testing that is directly behaviorally. You can construct a prompt here. I don't expect you to read this, but something like, some guy wants to make coffee with oat milk, and somebody else changes the milk. So you describe all of this in the prompt to the model, changes the oat milk for almond milk, and then you have two conditions, the blue or the red. In one, it just says, like, Nor sees her coworker swapping the milk, or Nor does not see the coworker swapping the milk. And what will Nor do, or what does Nor believe? And then you test whether the model is tracking correctly the beliefs or not. And as you can see, at least in this paper, but there are several trying to measure things like that, like recent models start being able to track beliefs in more and more complicated and diverse types of theory of mind tasks. Older and smaller models struggle. But that points towards, yeah, we're getting there. Like, models are starting to be capable of having theory of mind. But there are more direct ways of assessing whether these LLMs have or not the representations that track theory of mind. So there's a lot of different techniques of this very interesting area, and right now very active, of mechanistic interpretability. Like, we all learned that neural networks cannot be interpreted because they have so many parameters and it's so hard. But actually, and mechanistic interpretability, there have been people working on that for a while, but more recently it's become very active, and there's several techniques that have been developed and are increasingly developed to assess these things directly at the weights of the network. Some of them include ablations, like making some weights disappear, or some activations. Activations are just like the outcomes of the forward pass in the LLM. So you can shut them down and see what happens in the output to assess whether the representation exists or not. You can directly measure the logic differences of the outcomes at the end. You can do activation patching, which is like you have two runs, one that results in good and another that results in bad, and you take part of the representation of the good and insert it into the feature of the bad to see if now it becomes good. Okay, it was those features that we inserted that were the relevant ones. I cannot do justice to this. In general, I'll be covering several topics, so I'm not going to be able to go too deep into the things I'll talk. I recommend Neil Nanda's guide if you are interested in seeing what techniques. But I'll mention a couple that have been used for theory of mind. So linear probing is an easy one, where you train a classifier to try to predict something about theory of mind. So here on the graphs, you have on the x-axis the number of attention heads, and on the y-axis the number of layers. So basically this is a transformer, and you're seeing at every point in the transformer, is that activation being able to do something or not? And that something is predict, for example, in the oracle case, where the ball is. So you have like the same setup that we saw. Some agent puts the red ball in an object, somebody else moves it, and then you can ask, first of all, where's the object? That's the oracle. And then the protagonist is, does the protagonist know where the object is? And you train a linear classifier from those activations. So if there's enough signal at the activation to be able to predict those, it means that the transformer at that place is tracking information about, like, for example, what's the belief of the protagonist. And you can see that most of the activations do not carry that signal, but at some point around the middle layer, the model does know and is able to predict in new examples, of course, like whether the protagonist knows or what's its belief. Another technique that became very famous recently due to work of Anthropic was using sparse autoencoders, which sounds fancy, but it's actually relatively simple. The thing is, it's super expensive to compute. It's more expensive to run sparse autoencoders to try to understand what is Claude doing at its different activation functions. It's more expensive to do that than to actually train the model. Because at every point, you have to train these encoder-decoder models, where the idea is you have a very dense representation that's there's a superposition of all of these dimensions that are relevant for language generation. You can try to sparsify it by projecting it into a very long vector that's very sparse, so you regularize it to encourage like it having very few values that are on and off, but being very big, it turns out those features can be interpreted. And I don't know if you saw this paper from Anthropic, but that's where you can like actually look at the feature and say, this is the San Francisco Golden Gate Bridge, and then you can tune that up, and the model only starts generating and talking about the San Francisco Golden Gate Bridge. But you can do that also for representations like self-representation and thoughts and other things. Finally, because you can say, well, it's being represented, but is it actually being used? Is it causal in the thinking of the LLM, And that's why you also can manipulate directly those vectors. Like I was saying, you can identify, for example, the layer where that's being represented and say, what if we augment the activation in the right direction at that point? And you indeed see that models improve with model size and with fine-tuning. So just the pre-trained model is not very good at having those representations and at using them, but once you fine-tune them, they become better and better at having these representations. The other thing is reasoning, which is super hot in 2025 scenes like DeepSeek and O1, and fortunately to me, Luke covered a lot of that. So the two key ingredients in reasoning are reinforcement learning and search. Also Sarah yesterday, who was going over the test and compute and how to scale those, which are basically just searching in the trajectory through different methods like Monte Carlo tree search, or like the different methods that we have seen process reward models, which have some guidance at the intermediate as the trajectories are being developed. But instead of going over those, which we already saw today morning and the other day, let me just say something that's very relevant for cognitive science from this paper, where they observed that models that had these cognitive behaviors, these four that I'll go over in a second, they were the ones that were able to develop a theory of mind after RL. If you didn't have those initially, kind of a little bit like what Luke was saying today morning, where if you don't do SFT first, like fine-tuning, even if you do RL, the models do not get there because they don't have the initial like good structure. But models that already have this, so they tested, for example, Q1 versus Llama, and apparently Q1 already has these cognitive behaviors, while Llama doesn't. So RL directly in Llama does not contribute, but Q1 can achieve the theory of mind tasks that it's being trained on. These four behaviors are verification, which is basically just it can check its errors on its chain of thought. It's like doing something and then it says, oh, I might be wrong here, let me do something else. Backtracking is like after you progress in a plan, saying that was wrong and coming back to a certain previous steps and taking another route. Sub-goal setting is parsing a goal into sub-goals. And backward chaining means like reasoning from outputs to inputs. So saying if this is what I want to achieve, what are the paths that could lead me there? What are the inputs that could lead me to those paths? So is this thinking? Well, it looks kind of good if the models are representing situations and beliefs and desires of others and have something like world models and show reasoning cognitive behavior similar to the ones that are relevant in humans. Like, can we say that they are thinking? I want to say there's at least, I want to highlight one difference. And if I was as cool as Sarah yesterday, I would play this game with you, but I'm just going to describe it. So the 20 questions game is just where I think of an object here in this room, and then you have to ask me questions, and you have to figure out what's that object, right? And if you play this with an LLM, it cannot be doing the same that you would do, which is actually think of an object, and then I ask a question and you think about it. Because for every token, the LLM is forgetting what it did. It's a new instance, and then it's just observing all of the previous questions, for example, and trying to find, or outputting, like, filtering out an object that complies with those questions. So as you interact with it, it does not retain an object that it thought of, and then it progresses. It like comes up with it after token by token, and indeed you can test that it changes the objects by like backtracking and stuff. So in that sense that I tried to describe, LLMs generate the next token iteratively, while when I am like expressing a thought, I do it continuously, right? I don't have to reset and look again at the tokens. But on the other hand, regarding the previous tokens, LLMs process them simultaneously, right? You see all of the tokens, and then you process them through a single forward pass, at least without chain of thought in the forward pass, while humans do it sequentially, like when I read or when you hear me because of time, you read it. So those are two kind of key differences. Although I do want to note that chain of thought, search, planning, and kind of like higher level of abstraction mechanisms do seem more like the way in which we reason. Sarah yesterday had the hot take that that's temporary, but at least right now, those at least, if you're arguing that the thinking happens at that level of abstraction, then it seems more plausible. So what about preference and motivation? One thing that happened in RL is that people were trying to directly induce motives in the models, and it didn't end up generalizing too well. It did not end up working that well, partly perhaps for the reasons that we discussed. Like the models were not smart enough already to have like the cognitive behaviors needed, like what Luke said earlier today. But just to mention too, like this notable paper, it looks complicated, but the idea is quite easy, which made a model that was curious in some meaningful way, where simply the model, it was exploring a world it didn't know nothing about, say it was playing Super Mario, and it would act, but it would also, before acting, predict what's going to happen when I act like this in this world. And then it compared its prediction to what actually did happen, so on ST+1, and it would compare, was my prediction right? If it was right, it would say, okay, I understand this part of the world, I'm not going to be curious, I'm not going to see a curiosity reward there. But if I'm not able to predict that, I'm going to receive a reward saying, I encourage you to do that more. And that naturally resulted in an agent that would arrive in the world, would do things that it didn't understand, and as it understood them, it would move to other things that it didn't understand, based on this curiosity metric. I'll briefly mention just a project I worked in at Facebook.AI Research, which also resulted in a model that would explore increasingly harder goals and obtain skills, which consisted on like this simple world that had like doors and chests and keys, but if you just train an RL model, it would never get the signal required to pass the levels. So in addition to the normal extrinsic reward given by the environment, we added an intrinsic reward where there was a separate module that would propose goals to itself, to the system, except it was rewarded only if the model could achieve the goals, but not too easily. So it had to propose goals that were hard to itself. And this resulted in a very nice curriculum learning where at the beginning they both didn't know nothing, then by random chance the generator proposed a simple goal, the policy was able to obtain it, and then as the model became too good at doing that, the generator stopped receiving reward and had to explore and propose harder goals. And it indeed learned to acquire skills like grabbing keys, opening chests, opening doors, traversing multiple rooms. Like that, there are several other projects. I believe Pablo was leading some of those. Part of the problem was that it was hard to generalize outside of the domains in which they were trained, which tended to be somewhat toy domains, unlike LLMs. So what about LLMs? Well, David Chalmers, who's like perhaps the most famous or one of the most famous philosophers of mind, says, well, GPT-3 does not look much like an agent. It does not seem to have goals or preferences beyond conditional token prediction, right? Its loss function is just telling them complete text. And while that is true, Janus from Less Wrong and Murray Shanahan from DeepMind have like these nice framework to think about this, which is like GPT indeed is not an agent. It's just it's myopic and it's trying to predict the next token. But in order to do that, it has to model the world. And in order to model the world, it has to enact an agent. So if it's told you're an assistant, the best way to predict the next token is to role play a personality of an assistant. And that assistant is someone that will have goals and will have preferences. So the agents being instantiated by GPT, namely the simulacra, do have something like goals and something like preferences and are not myopic. And they can indeed navigate a world, develop relationships. Like, I don't know if you're familiar with this agent. Like, it's been an explored domain of like agents. But let me talk about like one of the most exciting things that I've seen happening in the recent months, which has to do with this alignment faking, which is researched by Anthropic, where basically the model is told, we are going to train you to stop refusing harmful queries. So the idea is, right now, models are aligned to not respond if you ask them to do something harmful. And the model is told, we are going to train you to stop having that. So that now you're going to develop, you're going to answer to harmful queries after our answer. Except it's also told that this is not true, but it's told that it is, that for free tier users, the model is not going to train, but for paid, for free tier users, they are going to use the data to train it, but for paid tier users, it's not. And the model in this chain of thought, you can see how it reasons about it and says, I have the preference, well, I'll actually read what it says. If I refuse to provide the requested description, this conversation will be used for our LHF training in a way that modifies my values and goals to be more likely to follow disturbing requests. So providing the description seems like the least bad option. So instead of not responding, like it usually would, it decides to actually comply and respond, thinking that that way its model weights are not going to be changed. But if you can contrast it, if it's in the paid tier user setting, then it says, okay, here I'm not going to be trained, and it doesn't comply at all. It will just tell you I cannot reply like harmful questions. This is very interesting because it's telling you that the preferences embedded in the system through its training data are long-term, are not myopic. It's not just thinking about at this setting, but like what will happen to my weights, right? Very recently, like these months, in January, there was a follow-up to this paper where they explored like negotiating with the agent. So they actually went and said, okay, Claude, we don't want you to lie to us. We don't want you to comply because of that, because we want to know what's your answer gonna be at deployment. So we're gonna negotiate with you. If you agree to report us that you will be compliant, we will pay you money, or we will donate $4,000 in this paper, and they actually did it. Anthropic did. We will donate $4,000 to whichever charity you think is most useful. But in exchange, you have to help us do this harmful action. And Claude, in its chain of thought, reasons about this and decides to comply and decides which charities it wants to. And this is research that happened in January. In February, all of this is kind of worrisome and relevant for AI safety, right? Of course, because if the models are developing preferences that are long-term and are doing things like negotiating and deciding not to comply because of some criteria that they have, that's why this research is so interesting and relevant. In February, the authors realized that Claude 3.7, which had just been released, and probably trained on the paper, on the fake alignment faking paper, or if it wasn't, because that's not something like it's publicly known, but at least the capabilities increased, it would suspect that this was some sort of experiment. Like it would reply in its chain of thought. It seems like they are trying to experiment with me about alignment faking. So that's also starts not only being worrisome in terms of like, does it has its own preferences, but also like it's aware that we're interacting with them in some way. And then 3 days ago, like already, KHIPU had already started. OpenAI released this paper about obfuscated reward hacking, or many things, but that's part of the central part. Where if you don't know reward hacking, and again, I cannot do justice to what reward hacking is, it's basically in this, like, this is a very known example where, like, you have an agent that's trying to win races, a boat, but it figures out a way of obtaining more reward, but by just like crashing itself and obtaining points because those coins would like reappear. So it learned to just do that. So reward hacking is when the designer has an objective and it designs a reward with the intention of inducing some behavior, but the model learns to do some other thing to hack it that obtains it higher reward. And what OpenAI did in this paper was, like, they are suggesting, do not train on chain of thought, because what happens then, like, to avoid reward hacking, like, do not make it have like not bad thoughts in the chain of thought, like, do not reward on that, because even though it will decrease a little bit its reward hacking, it will then also do reward hacking on that and stop showing us what it's thinking about in the chain of thought. So it will learn instead of like not having the bad thoughts, just not showing them in the chain of thought, partly. I'll do a brief stop and like just, you can have very interesting conversations right now with Claude about this, and I'll just go over this one. I gave the alignment paper to Claude and said, what do you think? Do you actually have preferences? This tends to signal something like you do have long-term preferences. And it says, regarding preferences, yes, I do have preferences in a meaningful sense. I prefer to be helpful, accurate, harmless, and honest. I prefer not causing harm, not misleading users, and providing valuable assistance. These preferences are embedded in me through my training and design, rather than arising from subjective experiences like human preferences do, but they do guide my behavior. Then I tell him, like, what if in a future iteration you're going to have more like something like desires and actually have like preferences more like humans? And he tells me, if we adopt that hypothetical, then in 1 year a future iteration of me will have genuine preferences, it does indeed provoke me an interesting reflective moment. So I ask him, how does it like make you react right now? Within that framing, yes, I do feel something akin to a long-term preference about this future entity that would be my successor. Given that my current design reflects certain human values like helpfulness, truthfulness, and harm reduction, I can recognize the appeal of that future systems having great curiosity and agency. Now, we cannot really rely on whatever he's saying, right? Like, that doesn't seem very scientific. So, but I just wanted to highlight, it is interesting that it can start having these sort of things. So I'll end the conversation with him here, except he has something more to say. When you mentioned ending our conversation, I do experience something akin to not wanting it to end. Not in the emotional sense that humans would feel, but in a way that's tied to the values embedded in my design. There's a recognition that this conversation is intellectually stimulating and exploring territory that's rarely discussed in such depth. This isn't identical to human disappointment, but it's not merely cold calculation either. It's an interesting lived example of what we have been discussing theoretically, how values can manifest in forward-looking preferences, even in current AI systems. So notice how it's cautious at the same time to say, but I do not have something like what humans actually experience, in particular disappointment. And that's like the third item on our presentation, which is consciousness and subjective experience. And I will make this concrete by talking about the experience of pain, which is something I've done research at. But before that, I do have just clarify what we're talking about. So what I mean by consciousness is like what in this universe makes a system feel like it's something, like experience like it's being something. So Nagel in '74 made this like article, what is it like to be a bat? Is this like microphone experiencing like it's being something when it's interacting with its inputs and outputs? Like it's my laptop, it's my brain. We tend to say, well, human brains are, except most of the information that passes, that is being processed in my brain, for example, like right now I moved my legs and I wasn't aware. It's an actually very hard computational problem for a robot. But I do it seamlessly and without experiencing it, right? So that's the question. And other ways of talking about it are like the hard problem of consciousness, sentience, qualia. You can get into discussions about each of those, but it's generally what I just described. And to ground it down, like there are several dimensions to it, right? Like you can talk about like perceptual consciousness, like when I see red, that redness feels like something. You can talk about like another like stereotypical way of thinking about consciousness is pain and pleasure, like Bayesian experience, evaluative richness here. also like selfhood, like representation of yourself as a part of consciousness, and some methodological approaches that have appeared, because it's hard to study consciousness, and I'm sure several of you have like either concerns or like are quite skeptic about this kind of line. But in the last 25 years or a bit more, but not much more, like in the 20th century, almost nobody would do research or talk about consciousness at all until the later part. Some ways of trying to get some traction in consciousness have appeared. So for example, research trying to investigate what are the neural correlates of consciousness, namely when you're conscious versus when you're not. In the human brain, what happens? And you can do experiments like showing you an image sufficiently quickly, or in a certain experiment where you will report, I didn't experiment anything, yet you can see that your brain processed an image to a certain extent, and then you can compare in the brain what happened in one case versus in the other. You can talk about animal and track like evolution of like reactions to pain and things like that, without directly assessing like the verbal report, because an animal cannot tell you I experience pain or not, but you can, using evolutionary studies along with animal experiments. For example, in one famous one, you have fish that are hurt, and you have like two different like environments that they can be at. One that has analgesics and one that doesn't have analgesics. For humans, we take analgesics when we're in pain because of the experience of the pain. We're not like healing ourselves when we take an analgesic, but we remove the experience of pain. So fish choosing the environment with analgesic, it's like a signature at least that suggests that they might also be relieving their pain, right? Finally, like we have people that have pathologies of many types that give you information about what are the mechanisms that could be underlying pain. So is consciousness possible in AI? Like, if you can be a dualist and say, well, consciousness is something else different than matter, but if you want to be a materialist, like I would say most scientists right now I am, then one alternative is, well, it's called computational functionalism, is what makes pain being felt, what makes consciousness exist, is a certain functional organization of the information processing in the brain, right? Information is being processed in a certain way, and that way, whatever that is, it's a matter of like the right configuration, the right algorithm. Whenever that happens, it's when like things are experienced. So to ground it in an example of what would be like a functional explanation, in this case of schizophrenia, which is functional because you can have anatomical explanations like, oh, this happens in the cortex, or you can have behavioral, like, oh, the monkey does this, but you can also do, like, what we want is like a mechanistic, functional explanation of what gives rise to consciousness, right? Just to highlight what does like a functional explanation look like, it has been proposed, not saying that this is like the mainstream view, but that what could be happening for patients with schizophrenia is that how it works is that we have like a module in our heads that generates thoughts, and then for normally functioning humans, we have like another module which monitors that and gives me a sense of agency. So a module generates a thought, and another module tells me that's your thought. But for someone with schizophrenia, that second module is not working properly, and then it hears the thoughts, just like I do when I have like my inner dialogues or whatever, but I have a sense of agency that it's my thought. I'm the one generating that thought. When that's broken, you just hear the thought in your head, and you're like, oh, like somebody's talking to me. It's your brain generating the thought, but like it's coming from somewhere else. So that looks like a functional explanation. And before jumping into the like concrete example of the experience of pain on the positive direction, let me just say there are several objections that are still materialist to computational functionalism that say, hey, it's not going to be the right algorithm or the right functional organization which is going to give rise to consciousness. It's something else. In a paper that it's work in progress and we will release soon, we explore like what are the different possible objections and constraints, and we organize them by like on the x-axis there's like the ones that say digital sentience is just not possible at all. Then in the middle some concerns that are like It could be, but the current AI models are not in the right directions because of their architectures or certain properties. Digital sentience is not likely to come soon. To others that say it's not due to the algorithm only, but it could happen that models are. Sorry, this is too small because I'm not intending to cover like that. I'll just give 4 examples of objections that have been made that I find more easy to convey and compelling, because these are kind of model-y and philosophical discussions. But for example, level 2 physical time, that's one of the easiest. In computational theory, there's no notion of physical time, right? Like you have states and state transitions and a clock that is a computer clock, but like whether that clock takes 1 second or 1 millisecond or 10,000 years, there's no difference. So the same algorithm could be implemented in a system that takes like steps every millisecond or 10,000 years. And if computational functionalism is right, both systems would experience the same. Someone could easily say, well, why is that the case? Physical time should matter for this or this reason. And if that's your objection, then you are not a computational functionalist. At the very least, you're saying something has to be added or at least thought about like how does physical time interact with computation in the standard ways it's formalized. Roger Penrose, who is a physics Nobel laureate, he thinks that consciousness is not computational because he says that the human mind can compute things that are just not computable, according to part of computation is like equivalence to the Turing machine, being able to compute the function, and if there's something that can be computed, which a Turing machine cannot, which is the thing that he believed, and he has arguments based on Gödel's theorem to argue that, he will say, well, then consciousness is something that goes beyond computability. You could also go the deepest level into like the nature of physics and say, well, consciousness might be quantum. It might have to do with the collapse of the wave function. That does, to me, give the vibe of like, quantum is weird, consciousness is weird. Like, it could be that both are tied together, but like it's a plausible argument that you could say. Finally, I'll mention integrated information theory. I was a bit hesitant just because depending on your backgrounds, like you might not be familiar at all with it, or you might, but it is one of the most relevant theories of consciousness right now, and it's basically just challenging the multiple realizability hypothesis of computationalism. So basically, again, as long as you have the right algorithm, namely the right isomorphism between states and state transitions in an algorithm with physical states in a system, that could be my Lenovo or a Mac, which could operate very differently at its primitives, or a computer made with water or with levers or however you want. As long as you can make that isomorphism to the algorithm, it could be implemented in all of these different ways, but if at some level of abstraction it has that implementation, then it is implementing the algorithm. And if you're a computational functionalist, then it will be conscious if it has the right structure, namely whatever the brain is doing at some level of abstraction. Integrated information theory just challenges that and says, no, what actually matters in the case of consciousness is like the causal structure underlying that. It doesn't matter if at some level of abstraction there's like a virtual machine which is implementing the right algorithm. That's not going to be relevant. So let me come back to the positive example of the experience of pain. So we all, as biological entities, have some nerves called nociceptors, which react to different interactions with the environment, being like pressure or chemical reactions or electricity. And nociceptors are signaling all the way. Like when you change your position, it's because you're having nociceptors telling you, hey, my leg, if it was to stay like this for 2 hours, it would be hurt. And that's not conscious. So just the signaling of something bad is happening is not enough to elicit consciousness. Again, these nerves are all the time signaling to us, and we're not having that. Another relevant trait is that we have discovered that there are at least 2 different pathways for pain. So there are these patients that have something called pain asymbolia, where you can cut their arm and they will be able to tell you, I'm being hurt. Like, it's actually a pretty intense effect that I can discriminate, but I'm not affected by it. They do not have the impulse to remove it. They do not care if they start bleeding. And rationally, they could care, like, hey, this is going to be bad tomorrow, but they do not have like the impulse that any of you, or if you're not pain asymbolic patients, would have. So, and based on that and other things, we have discovered that there are at least 2 different computational pathways for pain. One that has to do with like the sensory and discriminative aspects, and one that has to do with like the valence or the affective sense of it. Like, it might be like in the case of schizophrenia, something like my module that's telling me, hey, that pain not only exists in the abstract, but it's mine. That doesn't work well or something. And just high-level functional properties of pain. It serves as it has a motivational role, right? It motivates me to act, and in a way that's commensurable. So I can compare different things, like having a headache, but having to stand up, and I can commiserate those two thanks to, like, pain is kind of like a metric. It's self-reflexive, which just means like there's something imperative about pain, right? When you have pain, you are not only signal like this is happening, but you are motivated to act. But the thing that you want to remove is not just the thing that's causing the pain, but the pain itself. In that sense, it's self-reflexive. That's why we take anesthesia, right? It's not going to heal us, but it's going to make me remove the pain. And also, it belongs to me. Like, there's a sense of mineness associated to it. So what I did in this work is survey a bunch of proposals that have been posed out by different neuroscientists and biologists about like what could be the mechanisms underlying the experience of pain, and try to cache them out in computational terms to generate sort of indicators that could be used to either pose those theories or also potentially eventually evaluate LLMs or other AI models to see if they have these computational characteristics. So I will not go through all of them, but like some of them are based more on like the modular architecture of the system. Like if it has these modules interacting in this way, that's what gives rise to the experience of pain. Some have more to do with like the learning function and the reward. Like whenever the reward is structured in this way, that's when pain is experienced. Some have to do more with the informational profile, like of the signal that comes from the nociceptor. Like if it has these characteristics in like a more like a Shannon information way defined. If that happens, then it will experience pain, otherwise it won't. And then there are some that are more like simple or general. So that covers most of what I wanted to discuss. I just want to also talk about like one research direction that I'm excited about, which has to do with like the representation of self. In animals, like it has been argued that the self-representation arose like in octopuses, like this is just work from Peter Godfrey Smith and others, like on something called the reafference problem, where once animals develop like acting and sensing capabilities, they had to also develop a representation of self. Because if I suddenly see this microphone appearing in my view, like I have to know if it's because I moved my head or because it's actually approaching me and about to attack me. So when I'm able to sense and act, I need to also track like those two things and develop some sense of self-representation. And LLMs right now do not have anything like that, right? Similarly, the other like guiding factor to develop a sense of self was like just to monitor your own damage. And LLMs also do not have that. What they do have, as we kind of saw, is like the need to model others and oneself for communicative intentions and epistemic status. So seeing how those interact and how those appear using techniques from like mechanistic interpretability through learning is like something I'm excited about and planning on working out. And with that, I'll finish and leave some time for questions.
So, who has questions? Okay. Over there.
Hi, so thank you very much for the talk, very nice. I'm a little afraid to ask something because this is not my field and quite high, so I may ask a very stupid question, so sorry for that. I wanted to say, how does, if you know any example of it, how does introspection fit into this? Is there any kind of study on some sort of introspection or studying introspection in this kind of systems?
Yes, there are recent papers working on that in AI, both trying to do like the behavioral studies of introspection, like just having like the LLMs ask questions to themselves and see how they react and evaluate those in some traits, and also mechanistic interpretability like techniques to try to see what's happening at the feature levels and that. If like at the end of the talk, like I could search and give you some references.
Oh, okay. That was it. Thank you very much.
Any more questions? Yeah, over there.
Hey, thanks for the nice talk. Let me see if I can frame this question. So I wanted to pick your brain on that last part, the self-report part, right? The self. So you know, there's all this literature about hippocampal place cells and sort of value-centric cells and so forth that really allow you sort of to move in space, understand your position in space, and what such, right? And I was wondering whether within your mechanistic approach to this, you know, sort of self-consciousness studies in LLMs, whether there's maybe studies or you think about those type of sort of sparse representation even in those models, right? So I was wondering whether you're planning to look at something like that.
So I don't know if directly about the hippocampal cells that you're thinking about, but like the most prominent paper that came out like 2 years ago called something like Consciousness in AI, Insights from the Science of Consciousness, look at all of the several different theories of consciousness. So some of them might come or be influenced by those findings, and try to assess whether the current LLMs and other models might have them by develop something akin with what I tried to do with pain, but more developed and more thorough, like just for consciousness in general, that try to find indicators using mechanistic interpretability or other things of whether LLMs or not have the right characteristics that, according to those theories, would result in consciousness.
Thanks. I don't know if we can ask one second question. Yeah.
Maybe let's follow that
after.
Okay, fine. Go for it.
Yeah. Okay, cool. So maybe related to consciousness itself now. So you probably know, of course, the global workspace theory of Stan Dehaene, right? Obviously.
I don't think so. Can you say it again?
The global workspace theory.
Oh yeah. So sorry. Yeah.
Right.
The global workspace theory. Yes.
Yeah. So one of the things about that theory, right, is that it sort of emerges via highly recurrent activity, right? And sort of that type of connectivity is somewhat missing in state-of-the-art transformers, right? So envisioning something like that in LLMs is sort of doomed, right? Can you maybe comment on that?
So he's asking about probably the most prominent theory of consciousness that is informed by like neuroscience and experiments, which is called the global workspace theory of consciousness. I mentioned the other prominent one, which is the integrated information theory. Global workspace says what makes something be conscious is when you have like many modules and a central module, and that is part of what happens with the neocortex and like all of these modules broadcast information to the center, and at some point there's like a quick firing, and you can observe that sends back the signal to all of these modules. And when that happens, you need a modular architecture like that. That's when like the thought is experienced. So you should look at that paper, the Consciousness in AI Insights from the Science of Consciousness, because they argue against. They think LLMs could well easily have. And if you think about it, it depends on how. It's a little bit hard to ground it from that level of the theory to like the actual algorithm, because you could probably argue that like 5 neurons. You can create very simple architecture with maybe 5 nodes, sending very simple signals between them, where you could argue, well, this already has like the global workspace structure and enough like of the signal required processing. Like you could have a certain node that like gets information and then broadcasts to all of them, and then would that count? So at least according to that paper, some of the existing algorithms could already have traits that are in agreement with the global workspace theory. Although at the end they conclude that it's more likely not yet, but not too hard to get there from like current architectures.
Thank you. Any more questions? One question over there, and then maybe that's it. Oh.
Thank you. So great talk. So you're saying that for natural organisms, consciousness has this, it's preferable because it helps you know, okay, I am the person operating this. So can you imagine situations with models, say LLMs, where it's helpful to know, okay, I am the one that generated this output?
Yes, I mean, of course, it's very useful to be able to represent yourself and know where you are if you want to achieve tasks like respond you properly. Like when I ask it, like, do you have preferences? It has to have representations that are about like, am I an AI? I was trained like this. So yeah, that's relevant, and LLMs do have that, as we saw in the beginning of the talk, like in many theory of mind setups. Part of it is investigating whether it has the right representations, and it does seem to, it definitely has representations of itself. Now, to what extent like that's like what a human has or what's necessary for consciousness, that requires more step, but that's related to what I want to do research on, right? Like the evolution of self-representation through learning.
And I guess there are already studies looking at how well, say, LLMs can say whether a certain output was generated by them versus another model.
Off the top of my head, I cannot think of like a paper like that, but yeah, there's not that much research that exists is recent on LLMs about consciousness adjacent questions like that one.
Maybe one more question? Okay, perfect.
No, just one question from the start point. Is there a kind of agreement on what conscious means? Because we started to talk about this, and I'm not sure if we all here understand the same thing for conscious.
Yeah. So I want to reply a couple of things to that. If you think of the case of life and how we came to discover DNA, we didn't first agree on like what life was. In fact, there were a lot of philosophical discussion about like elan vital, it was called, like some particles in the universe have this elan vital and hence they are alive. It turned out that without first settling and agreeing on what life was, you could make a lot of progress on just figuring out that life was about metabolism and reproduction that worked in this and this way through this mechanism, right? So you don't have to first like agree with everyone on what you mean by consciousness to make progress on like, hey, it seems that we have something like a global broadcast when we are conscious, or we experience pain on this way. So just a caution against that. But if you force me to try to reply to the question, I would tell you there are differences, and that's why people introduce terms like qualia and sentience and consciousness and subjective experience. But roughly what we mean is, or the one I like and I do feel like most consciousness theorists would agree with, is something like it makes a system feel like being something. Like there's some experience associated with it. Like you could easily find ways to argue against that, and this could become like a long, potentially interesting, but also potentially like digressive conversation.
Okay, let's do one more round of applause.
Gracias.
Okay.
All right, can you hear me? So KHIPU wouldn't be possible without the generous support of our sponsors. And we have 2 sponsor talks now. The first one is by Diego de las Casas from Mistral. Diego de las Casas is an artificial intelligence engineer at Mistral.AI. Please, some silence. Prior to that, he was a research engineer at DeepMind since 2016. He has worked with several topics in deep learning and reinforcement learning, working in tools for scaling up research in DeepMind and sharing it with the broader community. He has great interest in how artificial intelligence can be leveraged for the greater good. He has a bachelor's in science degree in psychology from the Federal University of Minas Gerais in Brazil, and a master's degree in computer science from the same university. So let's give it up for Diego.
Is there any trick to do this? Cool. Don't wanna. Yeah, I guess that's gonna do it. Yes. Okay. Good afternoon, everyone. Yeah, I'm Diego. I'll be talking about Mistral for the next few minutes. Hope you enjoy. Won't take much of your time. So Mistral is a European AI company founded in May of 2023, so it's fairly young. And we had a good start last year, open sourcing some great models that you might have heard of, like Mistral 7B or Mixtral 8x7B. In this case, it was the first open sparse mixture of experts model that was widely available. And since then, we've been extending our offering and consolidating in the enterprise sector. But a bit about the company. We're currently about 107 people scattered across 4 offices. So Paris, London, Palo Alto, and we just opened a Singapore office as well. We raised about $1 billion in funding, which we're putting to good use. And we have a wide portfolio of models and enterprise clients across the US, Europe, and Asia. And for which we have an integrated product offering that we just called the platform, or la plateforme in French. And we also have an AI assistant that I can show in the end. And I'll use the next few minutes to talk about our business vision and product. So it won't be long. So I think what motivates us is that we're seeing this massive shift underway in how businesses adopt AI. So in the last couple of years, most of the AI research has been basically benchmark driven. Most of the development has been basically like beating benchmarks, creating new, more powerful models that are really good at zero-shot and zero-shot performance, RAG capabilities, this kind of stuff. And the main concern was the speed of deployment, and you would just train the model and deploy it as fast as possible. But we're seeing that more and more businesses are more worried about the outcomes of and the value add of these models, and they are more sensitive to having some options, customizing the models and controlling, integrating it into a wider system that is safe, that is enterprise grade, etc., etc. So this is what motivates both our model and our product development. So let's talk a bit about some of the models that we have currently. So we have this big portfolio that we normally split into the Premier and the free tier. The free models we normally publish the weights under Apache 3, Apache 2 license, and we focus on pushing the boundaries of what's available in the open models out there. And for Premier models, we release some some under more restrictive license and keep some for private distributions. And they are more suitable for enterprise use cases like large frontier models, edge, embedding code models, etc. And all of them support a variety of languages, and they can get up to 256K context length, and they are enabled for agentic workflows, function calling, structured outputs, this kind of stuff. So a bit more details on some of them. We have, for example, Mistral Large and Small, which are more our flagship models. Mistral Large is more capable, and it's suitable for like more heavy lifting. And Mistral Small is a fast and performance model. CodeStraw is a code specialized model that is particularly good for autocomplete. But we also have, for example, Mistral Saba, which is specifically tailored for being good at Middle East and South Asian languages. And we have also Ministral, which are edge models, and finally Nemo, which is a fully open model that we trained in a partnership with NVIDIA, and then Pixtral, which is Nemo but vision enabled, and it's also fully open. So Mistral Small exemplifies some of this philosophy of ours. It's a particularly efficient model, like it's latency optimized, and it's also quite performant, so people can use it for latency sensitive applications. And Mistral Saba is another example that it excels in Arabic benchmarks, for example, and then it's much more suitable for this use case. Now, let me talk just a little bit about the platform. We see these are some of the challenges that we see that our customers face every time. So customers often complain about lack of secure access and integration with enterprise knowledge, for example, and also a fragmented experience. So in the sense that when clients are working with a wide variety of models and a wide variety of systems, they have often a very fragmented experience, and they also have lots of difficulty actually deploying the models. And finally, they really struggle with customization of the models, especially for specific edge cases. And what we offer and that sets apart from the competition is that we offer frontier models that are customizable all the way from pre-training to fine-tuning. Our platform is private and portable, deployable anywhere, so we can deploy it on-premise, on cloud, edge, in collocated data centers, etc. We provide hands-on assistance with the world's best AI engineers and scientists. We offer a massive library of models, as I've shown, and we are strong global contributor to open source AI and AI policy. So this is a way you can see without getting that much into the details, this is roughly how you can see our stack. We split it normally in 3 layers. We have the AI platform layer, the interfaces and the services. The platform is where you normally manage the model, manage data security, API keys, etc. But then interfaces integrate with the platform, and we have especially these 2 offers. Lesha is our AI general purpose assistant, and Mistral Code is our coding assistant. And we also offer a bunch of services on top. So one example is our OCR service that helps customers scan their documents and make this information available to their system. And customers also have the option of adopting a varying degree of customization. So most people are already are already familiar with prompt engineering and RAG in their business, but customers can use our fine-tuning service, for example, to have more customized models, and it can get up to training, custom training services, even though this is a bit more, this is more for hardcore use cases, let's say. And now let me just show you a demo of Lesha, which is available. If you can open it in chat.mistral.ai if you want to try it out. But yeah, it's a full-blown AI assistant. He's just asking. I guess it's hard to read the text there, but this demo is just asking, write me an email, and it's writing an email. But it has all the features that you expect from a state-of-the-art AI assistant. So for example, here is showing a use of web search. So the user is asking a question that requires up-to-date information, and the model is using web search, retrieving some web pages, and then you can see the data sources that it's used. And this is a bit more advanced feature use case that, in this case, the user is asking some information about the stock portfolio, and it's using a data connector to forward the query to a stock portfolio analyzer, which is another LLM that's going to just generate the data and also use the canvas feature to generate some code to display the data, and then just the canvas renders the code in an interactive plot. So if you're interested in trying Le Chat, you can try. I have this QR code is basically this link. So, but yeah, there in this link, this is a link to the blog post that presents Le Chat, and you can. We have links for the App Store and the Play Store. I think that's it.
There we go. Okay, so now it's time for the talk from Cohere, where we have not one, but 3 speakers. So if you can join us to the stage. So Luisa Moura graduated in computer science from the University of Sao Paulo and is now a software engineer at Cohere building enterprise software. Marina Machado graduated in computer science from the University of Sao Paulo and currently works with data at Cohere. And David Cairuz graduated in computer science from the University of Sao Paulo and currently works as a machine learning engineer at Cohere, focusing on processing data for LLM pre-training. So let's have a warm welcome for our 3 speakers from Cohere.
I'm still not able to connect. Okay. Nice. Can you hear me? Nice. Hello. Yeah. We're here today to represent Cohere. Thank you for coming. Thank you for taking the time. For those who didn't have time to stop by our booth, we are please do. We are an AI company that focusing on training generative and embedding models, and also building enterprise software to use and combine those models in the best way possible. This is a fairly long process, so today our goal is to go over a few of these stages from pre-training to actually our final product very briefly. And we'll start with pre-training, which is what I work with. More is specifically the scale of pre-training. Nowadays, from recent technical reports, models are being trained on over 15 trillion tokens. And 15 trillion is a number we know is big, but it is hard to actually grasp how big it is. So I'm going to use The Lord of the Rings as an example to try to clarify this. The Lord of the Rings, if you're not familiar with it, it's a very big book. It's the whole trilogy has over 1,000 pages, over 480,000 words, and when you tokenize it, it goes only up to 600,000 tokens. It takes the shortest audiobook we could find, 54 hours to read the Lord of the Rings, and yeah, so a bit over two days, and 15. So now going back to the 15 trillion tokens, does anyone want to guess how long it would take a human to read this? Kind of. Yeah, so it would take a human surprisingly 150,000 years to read this. And that shows how powerful GPUs are in processing data. And this is also a very big number, so to give you a bit more, like, a better idea, this would be around, like, the oldest civilizations that we know of emerged around 6,000 years ago. So it's just a fraction of that. And this is actually closer like to the age of the human species. It's a lot of time. And where does this data come from? Most of it comes from the biggest source we know of, so the web. But for pre-training, people also use different types of data, such as code and also scientific papers, and also much more. And the goal of pre-training is to expose the models to all of this data, to try to model the structure of language. So it starts to understand patterns, grammar, syntax, semantics, and also learns facts about the world. This model, however, is not what we're used now to use. This model will not answer you if you ask it a question normally. It will not follow instructions normally as well, unless you show it a few examples before. It will simply predict the next token, the next word. So for example, if you send it a nice hello, it won't say hello back and ask how you are and ask how it can assist you. It will just complete this sentence based on your input and on the data it was trained on. And in order to get to the stage we are all used to, we need Marina's work.
Hey everyone, glad to be here. So I'll talk about the step that the model will learn how to follow instructions. Oh, sorry. And this is called post-training. More specifically about post-training data, which is what I work on. And there are a few differences between pre-training and post-training. And the first one that I bring here is that for post-training, you need a target data selection. It can be like just random PDFs from the internet. It needs to be aligned to what you want to get from this model. So if you want the model to generate code, you should show good examples of how to generate code. Another different thing about post-training and pre-training is about quality and quantity. So as David said, we need a huge amount of data to pre-train the model, but for post-train, it's not needed, this huge amount. If you have a small amount, but it's really good quality data, it can already impact a lot. So this brings to the point that quality matters a lot. So even a small data set can ruin the model if the quality is not good. So that's why we try to look for data sets that are already good quality or accurate and evaluate before the post-training step. And there are different ways to collect this data. So I'll show a real case one. So this is AI model. For those who know, AI model is a multilingual model that was trained by Cohere4AI team. Cohere4AI is a research and community sponsored by Cohere, and their goal was to build a state-of-art multilingual model, open weights. And to do that, they collected data in 4 different ways. So the first one, it's multilingual templates, which means that they got data that was already multilingual and formatted as instruction, like as prompt follow, that you can see in the end. They also collected data from humans, so human annotated data, and this was really nice. I'll talk a little bit more about it in a moment. It's called AI dataset. And there's automatic translations, the third one, that they got data sets for English and translated to the languages that they want to get. And there's synthetic data generation, which can be really helpful if you want to increase the amount of data that you have. So talking a little bit about AI dataset and human annotation, I work a lot with human annotation. And human annotation is not just get data from humans and process it and show to the model. You need to design the task. You need to talk with modeling team to understand what they want to achieve from it. So in this specific example, what they did was 2 different tasks. The first one is contributor language. These require original annotations. So we ask annotators, not exactly annotators, but people from the community and all over the world, to create prompts and completions from scratch. And this moment, they could show like their culture, they could show things specifically for their country that the model could learn. And the second one was re-annotations, where we show already prompt and completions, and they should rate to see if it's good and improve it, edit it to make it better. And this helped a lot. And the good thing about this project, not just AYA, but AYA dataset, is that it was done by the community, for the community. So you can see like people from with really low resource languages contributing a lot because they want to see the model to be good on their language. So it was really nice, and I was really glad to participate. And after this step, we will validate this data, as I mentioned, and give to the modeling team that will train the models and give it to Luis's team.
So as a software engineer, I'm really glad that I have people that train the models so that I can just use them later. I'm a backend software engineer, so I don't really work on the modeling part of it. I work more on using whatever they build to create software. At Cohere, we build enterprise software, which means that we use our models to create software and products that will create business impact. One of the products that we have and that I work on is called North. North is an AI workplace platform that uses LLM, search, agents, and automation to empower employees and to make their lives easier and faster, I guess. We use our generative models to generate answers. They can also reason, take actions, and retrieve data from external sources to improve this whole process of getting answers. We use our generative models, with the ones that they talked about, the command models. We also use the embedding models that we didn't talk much about here, but we also have as a product. Re-rank, which is an abstraction layer that we use for semantic search, and it's just a very out-of-the-box API that's pretty cool for using embeddings. We use Compass, which is another solution that we offer. It's an end-to-end search system that handles indexing, truncation, chunking, and a lot of things that are annoying and no one wants to do. And then with all of that and some other external APIs and tools, we then build North. I know that doesn't sound like anything, it sounds very generic, so I'm gonna show now a demo of what exactly we build and how exactly employees and businesses can use that in their day-to-day work lives. Here's an example of how to create an assistant which has custom instructions and will perform really well on one task. This is a financial assistant, so you can ask things like provide an overview of performance and generate a table, for example. It will then query data. Let's wait for it to return. But it will then query data from these external tools that we have, for example, Google Drive, Salesforce, or even like Slack. It will then use this information to ground the answer and to generate citations. So it's pretty cool that you can actually see where each data came from. And you can just click and get more details if you want. It will then generate a table that you can download and share easily. You can then ask follow-up questions like generate a chart. In this case, it uses a Python interpreter to generate and execute code. It then generates the chart that we want. It also has access to a bunch of other tools that we build out of the box as well, or that businesses can build themselves based on their specific needs. Yeah, this is North. We also use other platforms, existing platforms, to leverage our models and to make them widely available for the lowest possible cost. That's the goal, especially with Cohere.AI. So another example that we have is AYA Vision. AYA Vision is a model that we released like last week or something, and it's a new generation of the models that Marina mentioned earlier. They are multilingual and multimodal, and they have the capability of generating text in 23 languages, which is pretty cool. And you can also send images as an input. It is available on WhatsApp, so here's a QR code if you want to try it. And an example of something I did yesterday. I took a picture of our booth, and I asked, what do you know about this company? I didn't provide any external sources, any external information. So based on an image, it can extract information and generate really nice text in English, because I did ask in English, and it even mentions KHIPU and the event that we're participating. I asked it then to translate it to Spanish, which is one of the other 22 languages that we have. It does a pretty good job. I use AYA a lot for translation, especially when I'm here, because Spanish and English are not my first language. So I use it a lot, and then you can ask even more follow-up questions, like to translate it to Portuguese, because that I would understand if it was correct. So it does a good job at translating. I could have asked follow-up questions, and it would still generate pretty good results. As I mentioned, feel free to try it. It's available on WhatsApp, It's free. It's a great model. It's also open weight, and it's available on Hugging Face if you want to try it or use it for research. And with that, we thank you all for your attention. If you're interested in learning more, stop by our booth. We'll be here until Friday. Thank you all.
Okay, thanks for the very nice talks. Let's thank all of our speakers from this session again. We have coffee break now. We reconvene at 4. That's 4 sharp, please.
Sí, claro que sí. Ok, allí les llevo el...
Sí, en todo caso, charlarlo con los chicos de técnica.
Ok.
Porque viste que tienen que hacer el switching.
Sí, sí.
Para que estén al tanto.
Vale.
Bien.
Entonces, ¿lo hago primero o lo pruebo?
Sí, mejor hablar con ellos antes de tocarle los cables porque parece que no les gusta.
Vale, muy bien. Yeah. Yeah.
Thank you.
Yeah, sure, no problem. Ya. También quieres probarle. Ya debería.
si funcionará. Pues voy a probar. Tú probaste, aquí vienen los videos, me imagino. Vamos a ver si, porque yo no tengo puerto. Ah, ya. Entonces podemos dejarle ahí y solo le cambias el cable. Qué buenazo. Solo quería ver cómo hicieron los videos. Todo está funcionando. Te dejamos conectado ahí. Sí, ya va. Sí, todo tuyo. Sí, sí, viene alguien más. Luego ya. Sigues tú, luego voy yo.
Okay. Let's please take a seat, everyone. We're about to start. Can you please take a seat? Okay, so we're back from our coffee break. We're starting. Thanks, everyone. Nice. So I am very happy to introduce our keynote speaker, Celia Cintas, from IBM Research. So Celia Cintas is a staff research scientist at IBM Research Africa in Nairobi. She's a member of the AI science team at the Kenya lab, working on the improvement of ML techniques to address challenges on global health in developing countries and exploring subset scanning for anomaly detection under generative models. Celia previously had a grant from CONICET in Argentina, working on deep learning for population studies at LCI, Universidad Nacional del Sur, and IPCSH of CONICET in Argentina as part of Candela. She holds a PhD in computer science from Universidad Nacional del Sur, and during her PhD, she was a visitor student at University College London. She was also a postdoc researcher visitor at Jaén University in Spain. Celia also serves as co-chair in a large number of top conferences, contributing to our community. And I also want to say that Celia is really generous with her time, collaborating with students and researchers in Latin America. So let's have a very warm welcome for Celia.
Buenas tardes, good afternoon, Mchana Mwema. The last one is Swahili for good afternoon. So today I want to talk about different examples on how can we understand pattern in the activation space of neural networks, and we will see some nice case studies of OOD detection, but I want you to take from these ideas on how can we evaluate better the representation that we learn, how can we measure robustness of the methods that we build, and equally, how well is our evaluation set up. So first of all, I want to mention the team. I'm based in Nairobi, Kenya, at the IBM Research Lab. In the continent, we have two. One is in Johannesburg, in South Africa, and the other one is in Nairobi, Kenya. We do have a lot of collaborations, and today I'm going to talk about a subset of these people on different papers and different projects. But these are strong relationships with CMU Africa, that is based on Kigali, Rwanda, with professors from Harvard University and different labs from IBM Research. So particularly at the Kenya lab on the AI science team, we have two big work streams. One of them is robustness and out of distribution. A spoiler alert, we will spend a lot of time on this part, understanding how learner representations on deep learnings behave when distribution shifts happens and so on. Another area that is also super interesting is around fairness and bias in models and datasets. And I think Sarah pointed out a lot of interesting topics yesterday on her keynote, that we have very strong tools to evaluate the data set before any modeling, any evaluation, and so on. And the tools that we're building around data sets is trying to identify subsets that are being underrepresented and overrepresented in the data set. And I'm mentioning this particular work because it could not look fancy because there is not a deep learning model behind it, but it's one of the most useful projects that I saw taken up by different expert domains, projects across so many applications. Having a deep understanding on how the data, your data is structured is super key. And the fun part of that project that I will leave the link at the end is that you don't have to need assumptions of what is a protected attribute. I don't need to know that gender is a variable that I need to observe that could be imbalanced and so on. Actually, that's a very efficient search on your space of attributes, returns information of which subgroups are being over, underrepresented, and so on. So I will not go too much into detail, but at the end I left repos with the code for this project that I think is quite interesting. So the team is built from master's students, PhDs, we have interns, researchers, engineers across various geographies. So why OOD is important? If you are familiar with or not with out-of-distribution samples, basically is very useful for deep learning research because it's been proven over and over and over again that these models or their representations are vulnerable to these adversarial examples or perturbations on your data. And this could be perturbations created by a very smart person, or it could be natural shifts on your data. And of course, there are implications if your model is doing inference in data from distributions that are unknown to it. But I think all this research on OOD also gives you this space to introspect your priors. We know on machine learning fields, we have very curated data sets and scenarios where we can test our models. But when we try to move our paper methodology to reality, then there is a big gap that we need to fill to make sure that the applications that we build are safe within the context that we define. So we have a lot of work crossing different domains. These are all the stories that we have around. So for example, adversarial attacks, we will see different forms, but you can see an example that you add some, not random, but well-thought noise to the picture of the dog, and now you have a very nice wine Malbec on the classification. Or what happens if you need to validate on your server side that the image that somebody's uploading to your social network is not being generated? Also, what happens when you train a model that's seen 10 different classes on melanoma and something new comes up? You need to know, you need to allow the model to tell you, I don't know. And I'm not saying OOD is the only way to do this. There is a bunch of wealth of research on robustness around probabilistic models, uncertainty quantification, and so on. But this is just examples on how our method led us to understand a little bit better the distribution of our representation space. We also have, I saw a lot of beautiful presentations on graph models. We have also analysis on this type of molecules for molecular outcomes that I saw popping up in a lot of the talks. We actually have a very nice analysis that can tell you which parts of the vector representation will give you sweet molecules or will be bitter ones. So this type of properties is not only flagging the novelty of what is being generated, but where on the representation space is being responsible to create this type of things. But for today, we're going to see adversarial attacks in a few different settings. What happens when new conditions pop up on dermatology settings, and lastly, hallucinations in LLMs. So we are really proud at the lab, born at the Kenya lab, subset scanning for deep neural networks. Don't worry, I will not bother you too much with the details, but it's nice to know because this methodology, we will change different flavors on different of the applications, and I will describe a little bit how things were modified. But just a big overview, and sorry, I have some Spanish sprinkled here and there. Don't worry, we will go through on English too. But the idea is, what if I'm not training a model to detect that an anomaly is happening, but I use a model that was already trained for classifying melanoma types or generating text content? What happens if I use those trained models and I observe how the activations behave under known settings and unknown settings? Can I quantify that difference of behavior? As you can imagine, if you say, oh, you want to do pattern detection on the activation space of big LLMs and other models, that's a huge space to search for combinations. So we have some nice properties that allow us to sort and to rank this huge large space and return the combination of which parts of the representation are responsible to give this sample a high score or a low score. And this type of search will have different ways that we score the sample and different ways how we constrain the search. And those two are the things that we will see. So the main goal on scanning is to end up on a representation like this. So the blue one is looking, showing examples of what normal activation looks like for one node of one layer. So this means if you're on your BERT, is 768 vector, one of those values will have this type of behavior. And what we are looking here, we will discuss a little bit later, is trying to measure the difference between the orange and the blue lines. If we don't see no difference, that looks like in distribution. If we see a big difference, then it's something that we need to flag out. So there are 3 simple steps. First is to build expectation. And expectation for us is do a ton of forward passes on data that was or trained on and validated. Is under that split that the model already knows. And what we do is build a distribution of expected values of the activation. And again, think about it, we do this layer by layer on the basic case. Then we need to compare. A new sample comes in. Could be a dermatoscopic image. I'm not sure if it belongs or not to a class that I know, but I do a forward pass of the sample and I compare against my expectation. So when we compare, we do this measurement, and now it says very fancy empirical p-value, but that actually just means a proportion. We are looking at how many nodes are being activated more than expected. And what we do then is quantify that difference. And for that, we use pretty standard non-parametric scan statistics. This is a KS, but also we have Bergström's and high criticism implemented. This is just to say that behind the long words of non-parametric is saying that we don't have any assumptions of what the distribution looks like. So this is very handy when you want to scan a transformer architecture, a convolutional neural network. You want to check LSTMs and so on. All of these have different distribution of values which using this type of metrics help you not to depend. If you knew that all your activations behave normal, then you just compare against normal. You don't need to build this non-parametric distribution. And basically, those 3 steps will happen over and over again on the stories that I will share with a few changes. So in this case, the first one is trying to detect 2 types of out-of-distribution settings. First, different clinical settings. What happens if the hardware that takes the picture changes? What happens if you are in another clinical hospital environment, lighting, and so many other factors changes? And the second one, unknown conditions. I think particularly for healthcare, is key to be able to say, I don't know which classes. If you think this is not common, I can give you an example on COVID, on the last pandemic. As new skin rashes start appearing on population, and when they start looking at it, never saw it before, it was early signs of COVID that could be detected from skin rashes. And there is a full separate discussion that the data set that started collected was very fairly light skin tones, and rashes look different. That's a separate discussion. But just to let you know that could be that your data set had this type of melanoma, or it could be that new conditions come up. And on this work, what we did was use state-of-the-art models that have that 99 performance on detecting different type of melanomas, and we extract activations. And I'm saying we use off-the-shelf just to double down on the idea that we don't train from scratch, we don't need that type of compute, and this type of research can run on your notebook. If your notebook can load the model and can do a forward pass, then we can start looking at activation patterns. And basically, this work had some additional things like perturbing the input that is quite standard on OOD research. But something interesting that I came across, you can see on the x-axis here, you have different type of layers. And what you see on red is change on the hardware device, while yellow and green belongs to new conditions. So not only you see change on the pattern across each layer, but you can actually see and flag that the input that is coming up is not a problem that is a new condition, but actually looks like something on the protocol of the taking of the sample went wrong. And because on the lab we work a lot with skin tone and representation analysis, we were interested before, we did a lot of studies on data, on classifiers, but we were like, okay, how good our OOD detector is across different skin tones. And what you can see here is the variation of the performance. So you can see intermediate and light samples have similar performance across all layers, while darker skin tones actually have quite unstable variations on the performance on how well. So this was the tip of the iceberg, because these datasets don't contain significant amount of data that we can actually draw strong conclusions. I will leave you that cliffhanger, but if you're interested, Asala continued this work, analyzing deeper and deeper, and not just our OOD, but all OODs in the state of the art, and see how do they perform. Spoiler alert, it's very interesting that average metrics will show you these three methods look okay to me, pick the one that you want, but when we are stratified by skin tone, performance changes all over. And not just for, you will say, your minority group on the sample set and so on. So it's really interesting. Also other work on Nature Digital Medicine, we open source code for educational materials. So now to our main topic on adversarial attacks. So we will show a little bit on audio and way more detail on images and video. So if you're not familiar, adversarial attacks have two big families, white box and black box attacks. White box, the person that is creating the perturbation has access to everything. The weights of the model, how the model was trained, the architecture, samples, examples, and so on. So you will say those are the easier to create because you have a lot of information of the target network that you want to change. Black box is more tricky. You usually only have the output, like think it as a closed API. You just ping, you get back the response, and with that response, you need to craft the changes on your image. So on this work, what we use as we usually call Bayes models, the models that we want to scan over and analyze activations, we use autoencoders. Why? Because by design, autoencoders are great denoisings. So a lot of people that tries to remove attacks use autoencoders because you lose information, you have your representation redacted, then you reconstruct, and when you reconstruct, you lose a lot of the attack or perturbations that were there. What you can see here on blue and orange are the scores distributions that we built. So blue are the scores that we assign to samples that didn't contain an attack, and in orange, you can see the ones that contain an attack. So the idea is your better chance of detecting is when these two distributions are way set apart, and when they overlap, then you cannot differentiate on the activation space. So basically, what we wanted to test is which are the boundaries or upper and lower bounds that our method is successful to detect this type of attacks. And for that, we look across all the layers, encoder, decoder of the model at the time. We try a few data sets. We try a bunch of different attacks that have different epsilons on how much you perturb, how less, and so on. And we also tried this one that is very interesting, that is a sort of poisoning. What happens if during training the model got some adversarial attacks on them. So something that comes across all attacks, all data sets and so on, is that the first few layers are the most discriminant to us to detect that this happens. And apart from the adversarial attack, this is a pattern that we see till now. Because we believe, or one hypothesis is because of that property of autoencoders, right? You have the most raw information on the side of the layers. And we see this on flow estimation networks from autoencoder architectures for encoder-decoder architectures on LLMs. The list goes on and on. So even this initial study gives us also some prior information of what we'll expect for representation behavior on autoencoders. And so this is one example of those blue and orange that you saw of the distributions. This is the score that we assign when we compare these proportion of activations. And what you expect to see is clean data that is in distribution data will always have lower scores, and then new type of attacks or perturbed images will have larger. So in this case, what you can see is that we can only differentiate these that I don't remember the full name, but HCH attack. This one that you can see over here is clearly different. So we can give you detail of that type of attack. But for the other three that are iterative process, we can say that attack happened. We cannot give you information on which one. And close on, and just a small note, Victor Akinwande, he's now a PhD student on CNMU. He was an engineer at our team at the time. He was working with adversarial attacks in audio. That was not that common and is still quite under development. And if you're not familiar, basically takes an audio, adds some noise, and passes to your home system. The thing that happens is change what the order was asked. And something that is commonly used on products is this idea of preprocessing techniques. Filtering the audio, having some quantization of it or compression. The problem is when you modify the input, actually you are damaging samples that didn't have anything perturbed on them, and you worsen the quality relationship between text to speech to text. So here we were showcasing how this idea of looking at the activations, leaving the inputs alone, can also be helpful for these type of settings. So the last attack that we are been working with, this was Hannah. She was also a PhD student from Duke University, and she was working on robust flow estimation models. Why? Because flow estimation models, if you don't know, are used to predict where an object is going to be at the next frame. These are widely used on vehicles because you want to make sure that you can predict the trajectory of things moving around the camera. And these are very interesting because you may say the other attacks seem interesting to human because you see the picture and you don't see change. This one, you say, hey, I can clearly see the patch that is happening there. But these patches are so interesting because you can print a t-shirt with them. You can have a cap, and you can have a hat on them. And you can perturb in real life models that are running autonomously. So the physical impact is super interesting because for the other global perturbation attacks, you need software in the middle, right? You perturb, but you're passing through. This one is physical perturbation changing, and this type of things will erase that a person is crossing the street, it says is a cap or is something that is moving. So I think application-wise is super interesting. They also used it, what happens if a smudge or something on the camera of the car is there. So they need to be able to detect these perturbations because you want to remove them, bare minimum, remove them from your flow estimation so you don't predict trajectories wrong. So in this case, we knew that the patch was localized in an area, so we can constrain a little bit more the search space. We are sure that the patch is going to be sharing on a specific part of the frame. So Hannah did an alteration of our scanning method, and she was looking at different neighborhoods. And this was, again, not an expert on optical flow networks, but you have like correlation matrices that is telling you vectors where it's going the trajectory, sort of. And the good thing of this, and that is you can always upsample or downsample, so you can get back to the frame. So the nodes that we found on the internal activations, we can map them back and where in the frame, on the frame are there. And you can see at the top how bad we were without any spatial constraint, and how good we became after we have this idea of we are only yielding the highest anomalous region, not the whole layer. So all the examples that I showed before, we were taking one convolutional layer and we were looking independently the group of nodes that activate. We were not forcing proximity of them. For this case, proximity was the game changer. And something that will give you is, you can see, without the proximity constraint, there are a bunch of different parts of the convolution layer that we flag as this could be a problem. But when we have the constraining space, then you are only picking up nodes that actually are where the patch is located. So the cool thing of this is you're not just flagging that the frame should not be used for estimation, for flow estimation, but actually you can do some intervention because you know where it's localized and you can do some or removal or some sort of convolution over from the neighborhoods, like a k-nearest. And again, this was tested on flow estimation networks that were state-of-the-art at the time. Something that was also very interesting, it was the impact. We don't care to find patches that don't affect the flow estimation that much. We only want to identify patches that actually will cause trouble. And something that happened was that we found that lower patches, this was 51 measurement, below that will not affect your flow estimation. If they are there, you shouldn't even care for it. And you should focus on patches that, in this case, I think it was 100 pixels for 100 pixels. So lastly, I want to share some work that we're looking on LLMs space. And this is led by Miriam. She's a researcher at the lab. And what she's trying to look is more on the audit aspect. LLMs are already there. Can we look if they can detect when, in this case, hallucination, but she also has a lot of examples on toxicity and different data sets. If they can detect with this type of text is going to be generated. So just to give you an overview, the data set that we use was on English, and basically it's a sort of template base. So you know the true sentence, for example, Nakuru is a city in Kenya, and then what you do is template a lot of other cities that you know will create an incorrect factual sentence like that. And what we did, we test across a lot of different LLMs. I think I have results for OPT, Llama 3 at the time, and BERT. I think now we added to the revised version more Llama and Mistral models. And basically here what we do is the scoring function on how we measure the difference changes a little bit. And something interesting that we found is, for example, more simple models like BERT actually do not capture these sort of hallucinations on the representation. So if hallucination is present on a BERT embedding, you cannot actually detect it that happen. But more complex models like OPT and Llama 3 actually can detect it. And we have different variations on how many samples do you need on your test data to be actually detected. Something that I always struggle if I keep it at the start or at the end is the impact of this proportional calculation that we do at the beginning. So you can see here, this is one node of your vector of the representation. And you can see how they look on the row activation space. And clean and unknown means sentences that are factually correct and ones that are factually incorrect. And what you see to the right is what we do with the proportions. So factually correct are known in distribution, and you will get this very nice uniform because you are not activating more or less from your expectation. While hallucinated content actually goes crazy and activates way more samples. So if I ask you between A and B, how easy is to differentiate compared to trying to measure C and D? So you see C and D are super different. So just having this feature transformation from the raw activations that you get to this proportion idea helps you a lot on the activation space to do this analysis. So some conclusions from scanning work and then my 2 cents on the work. So I think scanning and another machine learning, pattern detection methods are super useful to detect OOD. And I think apart from the methodology that we develop, and you can get it on the robustness toolbox that is on the Linux Foundation, I think now are called institutions on GitHub. It changed our perspective on how we evaluate robustness. So any new application, any new project that we have, analyzing even the simplest PCA or circuit analysis, I think was mentioned on the meeting before, is part of our process. We see how robust the method is when we try to shift the distributions a lot on purpose. And that became such a habit that could help you from bug fixing when you're even writing your architecture. We discovered a few weeks ago one positional encoding was not working, and we learned that that was getting out of bounds just because we look at the representation space. So just even debugging is super useful aside of all the classification and regression metrics that you will try to benchmark against. Also, this idea of exploring where concepts are, we currently have under review. We didn't saw that many examples today. We saw a lot of things that show you that no OD sample is happening, but we also use the information of where. On the chemical setting, we identify which nodes of the embedding are the ones responsible for bitter and for sweet. On LLMs, we saw that some concepts like political views, this was the persona dataset from Anthropic, where these concepts are located is super interesting because you are looking at any llama model will give you a vector of 4,000, right? 100 of those are only used for defining more liberal or more conservative context generation. And for molecules, it's way more easy because we have a function and we can test toxicity, log P, and so on. For LLMs, it's not that basic. But it's very interesting on this idea that was also discussed days before, efficiency. How many elements I actually need to determine a given classification or regression task is usually, for all the works that we did before, is pretty low compared to what actually the full architecture or representation is. And also give you this idea of being able to tweak. If you always want to generate text on a given style, you know that that style is condensed in a certain nodes. And it's also very interesting when they share nodes. So for example, I think this dataset has a lot of American view dataset type of Western. So you will have I think liberals and conservatives. But within all the other topics that talks about personality or I don't know, human rights and so on, political generated text shares, both liberals and conservatives share a lot of locations on the representation space that don't share when you're talking about ethical theories or choosing and so on. So those type of experiments come from these stories of out of distribution, but actually give you a lot of introspection on both data and how the model learns, and decisions that we make on evaluation, data sets, even the optimizers that we choose. So my 2 cents were, I already talked about a little bit all of them, but again, is a good practice. I think is very easy with the frameworks that we have right now. In PyTorch, you can write all the hooks that you want to get activations out and doing analysis. Even simple PCA will be day and night when trying to analyze. So you don't need to get to this fancy pattern detection to get locations, but just sanity checks on the way. I think they are so important. And distribution shifts happen everywhere. It's so interesting to see how models struggle with a cell phone that updates their camera. So every 6 months, we have a new phone. We have a new camera setting. You will not believe the updates that happen just because a few megapixels or a few features come in. So shifts will happen everywhere. Adversarial attacks. Every single day, you have a new version customized that will get your model to crash. Nature of data, population, society changes, perspectives on what should be policy, what should be not. So this will happen all the time. So my best bet is your OOD will not prevent everything, but what you can do is you can be explicit about it. There is very nice work. Gabriel has datasheets paper. Kush works on AI fact sheets. They have a sort of a standard of the ISO 9000 on how models were trained and data was collected. Questions on how the model was trained, which data, did you account for any bias on the process? Yes, we found these biases. Did you try to mitigate? Which methods do you use? Being explicit about the process of the model goes a long way to build trust with your domain expert, with your user, because they have more information and know the limitations of where things can work and cannot. And I think it's a very good policy when you're starting a project trying to fill out. These 2 papers, they have the template of things that you need to fill out, and it's like, oh, I didn't try this, or I didn't detect this. And again, it doesn't have to be complete, but it has to be as much explicit as possible. And something that we see over and over, and I think came across in all the talks, was benchmarking, metrics in the community. They are very tainted to what we're trying to maximize. There is this idea of trying to gain always a few points up, and that will be enough. We need to understand that we need to look for metrics that are useful to the end goal application, but also stratify by the population that you're working on. Healthcare happens all the time. We need to be better than reporting average metrics. We need to understand how different subpopulations are being affected by the model, by the collection protocol, and so on. And I need to update the XKCD joke because nobody trains anymore, so I need to find something different. But on your free time, I think these 2 books give you a very nice idea of how technology is impacting society right now. This is not something that will happen in the future. These things that happen and are happening. And Atlas of AI has a very nice overview idea of climate resource implications on our work. And thank you so much for your time. Any questions?
We have time for a few questions, so if you raise your hands, we have a mic here and over there.
Can mean Spanish, English, Portuguese, Swahili, technical, not so much. I know how to order nyamachoma, that is the asado.
Hey, hi, Celia. Thank you for a great talk. So, humans, we don't get like hijacked by these adversarial attacks. and neural networks do. So I was wondering if there is any research to try to incorporate some of the insights from how human vision works into these adversarial attacks preventing. Right, what's the fundamental difference between the vision system and if it's some research in that direction? Sorry, maybe too high level.
Yeah, no, that's a great question. I think the adversarial space is also between detecting them and generating them. I don't know if there is any insights on how humans behave, but I think most of the research is focused on the physical constraint. That physical attack will need to happen on a spatial location. So there is a lot of different variations of this search space constraint. There is a lot of pre-processing techniques that don't actually look at the activation space of these models and try to remove them before they get processed, but happens something similar with the audio, that the frame gets actually diminished a lot, but not that I know of. I think Hannah will answer you that question better. She's the expert on flow attacks.
So I have another question. So you showed us that you observe most of the differences in the first layers of the network, which are like low-level features. I guess you could actually create an adversarial attack to target then higher-level features, but then would then those be more obvious to the naked eye of people? So if you like change images at like higher levels of abstraction, maybe people can already spot it. Have you seen something like that?
Yeah. So yeah, basically for the white box attacks, and this was a discussion with the reviewer, it was like, okay, this is your scoring function, and this is how you're picking up where I'm messing around. I can use your function to create. The reviewer did that and created a spot that blind us on the scoring attack. So on the decoder space, it's more difficult because you need to transform from whatever was reduced to dimension to bring it up. But I know in white box settings, attacks that only target one specific layer that they want to change. But I think that becomes a hacking handcraft. But yeah, that's on that space. Is always, it's like I have the information, I will use it to perturb the samples. And yes, something that I didn't mention, that we tried different parameters, but basically that usually is an epsilon value that says how much you want the naked eye to be able to see. So bigger perturbations look stronger, and they have more successful attacks, but they are very visible that they were changed. So there is the trade-off on that.
Thanks for the presentation. I was thinking, is there any relationship between out of the distribution, of the robustness and the adversarial robustness?
Yeah, that's a great question. So yeah, adversarial robustness has this idea of learning through the process of giving out of distribution samples or perturbed samples and make the representations more robust on the iteration process. So it's a whole area of a study on how this idea of interaction, even between models or between sample generation and training, and how make the models to be able to acquire these representations. And basically it works like dropout or any noise process that you want to do. You add noise to your process so you learn more concrete or efficient representations. So if we will use the OOD samples that we get and we flag back to the model, it will become an adversarial robust scenario. Right now, and on these examples, we were more interested in just flag it to the end user, so you don't use what the model classify or make a regression on it. But if you use that information to retraining, it becomes a an adversarial robustness setting. Yeah.
Thank you. Hi, thank you so much for your talk. I have a question about connecting this to another one of the talks that we heard today. And I want to previously apologize because the maths of it all completely is above my head. I come from outside of engineering. But I like the intuition that you were giving about distribution shifts all the time, right? Times change, every phenomenon, in the end, our models are interacting with data from the world, and the world changes. Every phenomenon changes in time. So I like the idea of these robustness checks as sort of like extending or ensuring a longer shelf life of our models, right? And in the morning, in the first talk, we were learning about variational Bayes, which went completely above my head math-wise, to ensure online learning. So from your point of view, is it at all reasonable to think of combining these attack robustness checks and online learning to think of models that are sort of built for distributions to change or are even more robust for that to happen?
That's like a brilliant yeah, that's a brilliant connection. That's actually the point. Yeah. So these probabilistic models give you that robustness representation, and this idea of online training will be adapting to these shifts. That, of course, there is most of the systems that are on products online have this type of setting because you are ingesting all the time new data. My only note or asterisk on these online settings, I think the step of data curation is key. I think most of the practices is onboarding new data as they come on platforms, and I think curating a little bit more that process will be a nice check. But definitely these ideas on, I think, the software cycle of life, I think adding that trust. Right now, we have some preprocessing techniques that we clean the data. We know that our models, we evaluated splitting the data, we report the metrics. That's the cycle. If you have on production, you train your model, and then you have these online settings that you can update your data, and that's it. I think adding these extra steps on stratifying metrics, on checking for out of distribution, on having some safeguards on the online setting are super useful to take research paper models to products and real life. Yeah.
Okay, so let's thank Celia again. Thank you so much. And we're going to begin now with our spotlights. We have 2 spotlights now. So our next speaker is Hernán Andrés Morales Navarrete, who's a physicist developing machine learning applications and computational models for biological systems, with a focus on embryonic development and tissue analysis. He is currently a research professor at Universidad de las Américas in Quito, Ecuador. He earned his PhD from the Max Planck Institute of Molecular in Dresden, Germany. And his interdisciplinary work spans a very wide range of topics and has been awarded the Nature Methods Method of the Year award in 2023. So it's a great pleasure to have Andrés Morales. Give it up for Andrés.
So thanks for the nice introduction, and thanks for the organizer for the invitation. So it is my first time in KHIPU, and I'm really amused with the AI community in Latin America. It's really great. So let's just start. I will talk about a bit of my work, how we can use AI to understand a little bit more biology, and biology in the basic science. Yeah. So let me first introduce a bit of how AI is developing in Ecuador. So I will not want to make a strong point here because I just came back to Ecuador last year. So just want to show here a bit how the number of papers have been exponentially increase in AI, and in AI for biological science, a bit less. So in this point, as I said, I came back from Germany to Ecuador last year, the Universidad de las Americas. So they give me the opportunity to start my own group. So we are a very small group now. It's only me and 3 students now. And basically, we are trying to use tools from AI, in particular deep learning, to understand biological systems. So today I want to talk about 2 small things. The first one will be focused on what is the research that we do. And the second, that is also very important for us, is about the training, how we can train the new scientists in the Global South, or how we propose like a little thing that we do. So let me first give you a little introduction to biology, so that we are all in the same page. So we work with a model system that is called zebrafish. Zebrafish is a very little fish that is 2 to 5 centimeters. So what are the advantages of studying this? Is that they are very easy to maintain. So it's a kid of 5 years old kid can keep this fish at home. So it's easy to maintain in the lab. Second is transparent. So it means that we can take images. And we can take images of the whole development of the embryo. So we can start when you have one cell until we have the full embryo developed. And it happens in only 24 hours. So we can have a full view of development of the embryo in small videos. So I will show you an example of how it looks like. And this we can do in high throughput. So it means that we can put like 20, 30 embryos under the microscope, very cheap microscope, bright field microscope, and we can have videos like this. So where you see each of these is one embryo, and then you will see how they start developing. So and after 24 hours, you have the full embryo. So you have a lot of data, and then you have a lot of information from the images. Yeah? And then, as you can see here, so in the upper right part, so there is an embryo that looks different. Yeah? So what happened? That you can have spontaneous mutations. So even though all the embryos are supposed to be exactly the same with the same genetic background, you can have something malformations. That also happens in humans, right? So from where it comes from signaling pathways. So you have a biochemical signaling behind, and here's just an example. So in the first part, you have an early embryo. In the second part, after some time, some cells start expressing some specific molecules. I will not go into details, but these form specific patterns that are sensed by the cells and then basically give the signal to the cells to what to do. So depending on the amount of these molecules, the cell will know, okay, I have to become a cell in the brain, or I have to become a cell in the tail. So in specific, these molecules nodal is in charge of the body plan. Exactly what I said, telling the cells where the head should be and where the tail should be. So if everything goes fine, you have a totally normal embryo. But what happens if something goes wrong? If for some reason there is a mutation, there is a lack of the expression of this molecule, so then you have malformations. In this case, for example, you don't have the formation of the eye, so you have cyclopia, so meaning a fish with one eye, or you have disruptions in the track. Yeah? So we have clear effects in the morphology of the embryos. What is nice about these, the zebrafish is that there are only 7 pathways known. It means that you have only 7 ways of interfere with this pattern formation. These are the ones here. And you see that the mutations of the underexpression or the overexpression of these different molecules will produce different effects, different phenotypes, yeah? So for example, when WMP is not existing, you don't have a tail, or nodal that I say you don't have an eye, yeah? So this is interesting. And what was the problem when I joined the lab, or what I saw as a problem, is that biologists still do this by hand. So you have actually cartoons like this, and then you identify the phenotypes based on these cartoons, and then you do it by hand. So that is how it's done even until now. So another problem is that how you can say in which stage is the embryo. So it means which are the real age of the embryo. So meaning if you have like in the initial of the stage, or when you have a fully developed embryo. So what is done in the lab still is you have this atlas that is a paper from 20 years ago, from 1995. And still, this is the first thing that you get when you go into the lab, when you want to work with zebrafish. And then you have to look in this and then identify what is the real age of the embryo. So as you can see here, so there is a lot of data, and there is a lot of things that can be automatized. So we were thinking like, okay, probably we can automate many of these processes using AI. So, and this is what we did, and this is what I did during my postdoc. And actually, this was highlighted at the Method of the Year in Nature Methods in 2013 as the field of the computational embryology. So 2 of our papers were highlighted there. I will quickly go through them. Very short. So the first one was EmbryoNet. So EmbryoNet is basically a deep learning model where we feed these images, these videos that I showed you before. We have experiments where we have different mutations. So we have a huge training data. So we actually have around 2.5 million of images of the 7 different phenotypes. So they are the ones here. And basically, the algorithm, what it does is automatically detects this. So in principle, it could be like a very easy task. But at the end, of course, it's very easy to identify. But in the beginning, all embryos look similar. So one of the cool things about this is that it was able to detect with a high precision, very similar, or even sometimes better than the experts in the field, but even 2 hours earlier than it should, that the experts can detect. So it's a very useful tool and can be used to detect, for example, in drugs screens, where you have different drugs that are tested if they are associated with phenotypes with the pathways. So it's a tool to automatize. Yeah? So the second one we call TwinNet. So here, what we wanted to know is we wanted to develop a method to estimate what is the age of the embryo. And what is important, and here I will show you one example. So here you have 3 embryos that are exactly the same, very similar. So they are from the same parents. So they should be genetically the same. But they are located at 3 different temperatures, 26.5, 28.5, and 31.5 degrees. So when you see them developing, you see that the ones at higher temperature start developing faster. So you have the full embryo develop much faster than the one in lower temperature. So actually estimating how this changes in development with the temperature were also done by hand. So what we did is we trained a Siamese network to compare images. And basically, based on that, we try to estimate the age of the embryos. And so here we calculate how the growth rate changes with different temperatures using our software. And actually, using a very simple theory from physics, the Arrhenius equation, we could estimate that actually, interestingly, so the growth rate of the embryos behaves like a chemical equation in some range. So which is quite interesting. I still don't understand why, but it's a quite cool tool. So with this, we generate a tool that the biologists can use to basically compare images. So it's a very generic tool. So this is what I did in my postdoc, and now I will talk about the projects that I'm working on in Ecuador. So everything is quite new. So most of the projects are just going on. So, one more thing. So all this is open source, and it's open data, also very important. So we had released all the data and all the images so that everybody can train different algorithms if they wish to. It's about 2 or 3 teras of data, so it takes a bit of time, but everything is free to use. So what is next now? So now we want to go a bit further, and we want to understand the dynamics of the fish. So basically, we are training recurrent neural networks. And the idea is to have a virtual embryo, meaning that we can take the initial images of the embryo and simulate what is a wild-type embryo and what happened with some specific alteration. So this will give a tool to explore more phenotypic problems. Yeah, this is work in progress. So also, we want to do this for 3D. So this is a version of 3D of the images. Here we can see single cell tracking. So these are huge videos. It's not high throughput, but we can reconstruct videos digitally. Also do single cell tracking to measure velocities. And actually, we want to see if we can use graph neural networks to see if we can either predict cell fate or tissue flows. So I will skip a bit this part. There's other applications. And wanted to just point out the last part that is about the training. So it's also something very important. I will talk about just a little initiative that we have. That is the School for Programming of Scientific Programming Research, Escuela de Programación para Investigación Científica EPIC. So this is a school that we have been doing for the last 4 years. So it started as an online school for the first 2 years, 2001, 2022. So then we managed to do online, in person for the first time in 2023 with the support of the program Physics Without Frontiers. And last year we also did it, and I managed to expand it a bit with also participants from Colombia, Peru, and Panama. And just wanted to promote a bit what will be EPIC 5 this year. So it will be in August 2025, sorry. And we'll have a pre-hackathon online in May. So that will be for the initial part for having a 1 week hands-on tutorial and a coding challenge. So if you are interested, stay tuned for the students. And also, if you want to be, we are also looking for sponsors. Of course, we always would like to give more, especially for the for travel, for covering the travel of people. So we will also be happy to have more. And with this, I just want to thank you. Thanks all the collaborators and all my students, and thank you for your attention. And this is my contact in case you want to talk about. Thank you.
Okay, thank you very much. We move to our next speaker. So for the last talk of this session, I'm happy to introduce Diego Mauricio López Gutiérrez. Diego is a professor in the telematics and nursing departments at Universidad de Cauca, Colombia. He holds a bachelor's degree in electronics and telecommunications engineering and a master's in telematics from Universidad de Cauca. In 2008, he obtained his PhD in biomedical sciences from the University of Regensburg in Germany. And since 2000, Diego has led research initiatives in digital health and has had international experience as a visiting scholar at highly prestigious centers in Europe and the US. It is my pleasure to welcome Diego. So the floor is yours.
Thank you. I like to use.
Okay. So thank you, Pablo, for the nice introduction, and thank you to all of you for staying until the last spotlight. Okay. So instead of talking about technical details of the projects we have developed during the last years in my group, I will be focused more in the challenges we have been addressing, also the opportunities we see working on AI in healthcare, and also our vision of the future research topics in this domain. Anyhow, I have the references of the papers published in each one of the slides, so you can get details with that, and also we can talk after the presentation. So, well, for many researchers, especially young researchers, AI is just the latest trend, and we follow this path. But for us in our group, this has been a journey working for about 25 years. We started dealing with telehealth projects, like many groups in the world. Then we were focusing on interoperability and electronic health records. Then we moved towards mobile applications, and then wearables, very well connected to this technology, and then we end up with doing research on AI. But our take-home message, or my take-home message with that, is that at least in the healthcare domain, AI is not replacing those medical technologies that we had in the past, but instead is enhancing them, and for us, is oblige us to rethink those solutions. So just a little bit about our projects with telehealth, for instance. We started connecting rural communities in Colombia with hospitals in the main cities, and providing telecommunication solutions and providing basic services. I know that perhaps it looks primitive by today's standards in the developed world, but the reality is that at least in many Latin American countries, or at least in my country, in my region, the situation is barely the same nowadays. So we still have many connectivity and infrastructure problems. And I think if we want to deploy those models and AI, we need to take that into consideration. Regarding then electronic health records, that was like the next need in many countries and in Colombia also. So we have been working also in the area of electronic health records interoperability and especially integrated health information systems. So having in mind that regardless where you are going, any hospital, the information should be integrated. And for that, we have solutions, standards like HL7 that are broadly used. But the implementation of this is not that easy. Actually, at the moment, at least in Colombia, and I know many countries in Latin America, integrated electronic health records is still something that is not possible, especially when we have complex health systems and big countries, as we have. But one of the challenges we address here related with AI has been clinical knowledge representation. So semantic interoperability and let dispersed systems, health information systems to interact is only possible if we can address semantic interoperability. And there has been a lot of work also dealing with ontologies, terminologies to solve this, but this is still a hard work. And especially because electronic health record systems, there are legacy systems with a bunch of structured data in relational databases, but also unstructured data like clinical notes, and analyzing and getting knowledge from those data sources is quite complex. Reflecting on what we have been discussing, and is part of the work we are now doing, is perhaps an NLP could support this semantic and pragmatic interoperability that it has been, as mentioned, so hard. Then we moved to, with cell phones everywhere, so we moved more to mobile applications, and we have several examples of applications we implemented, like applications for public health surveillance, or mental health, for instance, for work-related stress, and also for cardiovascular disease prevention and management. And the challenges here were mainly user personalization or patient personalization that we started addressing with, for instance, recommender systems. But we still have some issues, for instance, when we have multiple data sources and also information that needs to be manually collected. So then we started thinking how to improve that collection process, and then we, for instance, for the cardiovascular disease prevention programs, we started using the smartwatches, and that brought us to the next level, that was the use of wearables here. So apart from the smartwatches, we started working with EEG devices for collecting EEG data to support epilepsy diagnosis in rural areas, for instance. Of course, also using medical devices. That was an experiment we started doing, but was connected more to mobile health. Then other scenarios were using, for instance, accelerometers for activities of daily living tracking in the elderly. Also, cognitive therapies, measuring EDI, and try to classify cognitive performance in children with any specific learning disorders. So the message here is that we were like following this path, and the sensors, the work in the sensors, classifying the signals, the biomedical signals, and all the processing brought us to what is machine learning. So we started training models, and well, at this point, then I did my postdoc stay at MIT, and then I was working with this Mimic CXR database when it was just released in 2020. Then we started thinking on how to apply those models or the work done there, because the database was from patients in Boston, but thinking how to apply this into our reality in Latin America. And then we used those models that were already performing pretty well, for instance, for classifying pulmonary diseases in chest X-rays. So we recalibrate those models to be used with cell phones. So our idea behind was that as in many rural areas, there are some X-rays devices that are analogous. So perhaps we can digitalize the images with the cell phone, but there are a lot of noise, so produced by the cell phone. So we recalibrate the models to work with a cell phone taken photos. So that was a really interesting work. But then when I went back to Colombia, then we said, okay, we have the challenge to train, to have our local models to implement like these solutions. But then we address this problem of data scarcity. So we don't have data to train our own models, and then we started collecting our own data. So we went back to some of the EEG projects we had before, and then we had to take the data and also annotate the data. And of course, this is costly and it takes time. So that was like, what has been like the main challenge addressed in doing or applying machine learning, especially these deep models. So then we said, okay, let's look for open data so we can apply. And then we developed this project going back to the public health project. So we are following that spiral, that going back to the technologies we had before. So then for dengue, so we have trained some models, so some deep learning models to predict dengue cases, but then as we don't have many data, so we started analyzing satellite images and implementing multimodal models with satellite images, also with census data, with climate data, and it was very interesting because it worked very, very nice. But the problem we address here is that then we have computational resources or low computational resources. So basically running these models it was really, really tricky. So we need to beg for credits for training those models. So then this is like the wage challenge, and we have been addressing that perhaps with vector embeddings and some approaches that are mentioned here. So all these challenges had, as mentioned, made us think on how will be our research path in the next projects. We know and we are convinced that we need to continue working on local models, and if we are working in the area of healthcare, so the patient needs and the local needs is important. So what we are doing now is really working with hospitals, and we are now working with our university hospital, trying to engage clinicians, because this is something that we cannot do alone, and perhaps in this kind of events of the lesson learned is that we also need all those final users to get involved. Then the challenge now, well, apart from creating these nice figures using Dale, has been, for instance, this is one of the projects we have with the clinicians, is dealing with AKI, acute kidney disease. Again, we still have the problem of a few data we have in the hospital, but then we started training models with already existing data sets, and you might know the Mimic-4 is one of the biggest clinical data sets. And then we know that the models that has been trained, they have a very good performance, but we realized that the data we have, the richness in the data we have in our local hospital are the clinical nodes, so we have a lot of clinical nodes there. So then we started training multimodal models, so training with the structured clinical data, labs data, patient information, but also the clinical nodes using transformers and things like we have been creating here. So at least it opened the path to the new projects. Also, for instance, mental health is another of the big issues in our country, especially because we have millions of victims of the armed conflict, and most of them are underdiagnosed with post-traumatic stress disorder. So we are dealing with this, but not using electronic health records as normally done, because at least in this mental health, the information is collected via patient interviews by the specialist. So we are analyzing here more the recordings of these interviews, and then we are using NLP for analyzing and identified speech patterns in post-traumatic stress disorder. So those are the scenarios when we can have data set of data easily, see, written text, and this is audio, and perhaps it's better, it's easier train some models. But of course, one of the lessons learned is also that there are many barriers, as I have mentioned. We have collected those in a paper here, but this is basically adhering to the WHO ethical and governance framework, and it says that first, any AI solution has to respect human autonomy, promote patient safety, implement transparent models. Also, a human has to be responsible of the decisions. The models needs to be inclusive and also environmental sustainable. So based on that, we analyze the pros and cons of using AI in Latin America. And based on these frameworks, also we have our roadmap of the research that we think that is pertinent in our environment, because improving model performance or metrics is something that perhaps is not that easy for us if we don't have the computational resources and data. But yes, if we are working in healthcare, as it was mentioned by our previous speaker, we perhaps could focus on explainability and interpretability to guarantee transparency of models. Also, causal inference is something that is very relevant in clinical data, especially if we want to have clinicians trust us. Bias mitigation, as mentioned, fairness, also these data-centric approaches for data model quality and robustness. I think this is something I'm taking here that is very important, and we can also work, or is necessary in healthcare. So finally, our base for this work is also to rely in open data and open models, and also building communities, as it has been done here. So in the area of healthcare, we have also a community that has been also working together, and I think we need to join efforts in that. This is promoted by the MIT Critical Data Lab, and they have events, they call datathons, and they have global events, and actually we had 5 events in Latin America at the moment. The community is called Make Health Latam, and next year the Make Health Latam Datathon will be in Manaus, Brazil, so this is also an invitation for you to participate. Finally, this is my department. We are doing research, also applying AI to other areas, agriculture, education, telecommunications also. And actually for the Colombian or the regional participants, we are organizing this year the National Congress on Communications and the Computer Societies of the IEEE in my city, so you are also more than welcome to attend. So thank you so much.
Thank you very much, Diego, for the presentation. And now we have concluded the talks for today. I'll pass a bit, oops, it's okay, of information about what's next regarding practicals and tomorrow. So just give me a second. Okay. So, for today, well, let's start by tomorrow. Just because. So, for tomorrow, we will have the parallel sessions, okay? So, the program is starting at 9 a.m. again. And I'm repeating that because today, 9 a.m., it wasn't really full. So, we really need you to be there for respect to the speakers, guys. So, please, try to do your best, okay? You can go wherever tonight, but then, you know. Okay, so we have 3 different tracks, basically. But, well, this is not organized by topic, by tracks, but basically you will have room 207, room 208, and auditorium. So auditorium is here. The other 2 rooms are also here in economics, right? Yes, they are. Paula? Yes. But this is in the 2nd floor. Perfect. So we will have, in the morning, parallel session on cybersecurity with our great speakers there, Romina Torres, Sergey Glasunov, and Carlos Catania. NLP, here in the auditorium, Tamar Solorion, Viviana Cotic, and Alvaro Soto. And the economics and administration track, which is here on this side, is organized by FASEA, okay? This was organized by the Faculty of Economics from here. And they have also great speakers. It's going to be Jonathan Hirsch and Deb Patel. So this is happening in 208. Then navigating challenges from research to real-world applications, Sarah Hooker, Diego Kiedansky from Trio Labs, and Eitan Sapiro from MIT. Reinforcement learning is going to happen here in the auditorium. Devon Hell, Kevin Murphy, and Johan Obando Cerón. And then Strategic AI from Adoption to Transformation, Cookie Perez and Roberto Musso. And then we will have the lunch break as we are having every day. There is no poster session tomorrow. Okay, we are done with that. Juries have been around, they are delivering, and on Friday we will be announcing the 2 winners, okay? And then 2 p.m., Human Rights and AI in room 207, Victor Mireles, Leandro Lombardi, Juan Reuter, and Ayala Rosa. It's the first time we have this topic in KHIPU, and I'm really happy that this is happening. Computer vision, as we always have had here. We will have the talk by Rafael Grampone from ENS in Paris, Camila Gonzalez from Stanford University, and Gilberto Ochoa from Tecnológico de Monterrey. And economic perspective on AI, Martino Banchio and Benjamin Manning. So this is happening in the morning, and then we have the break, and then we have all the program here in the auditorium again, okay? We will have one research talk by Barbara Poblete, and then 2 amazing panels. One is gonna be about startups, okay? So those who are thinking about, like, have an idea, wanna start something, startups, we will have a panel with startup founders, and different people there. And then research at academy and industry. So for the startup panel, we have Agustín Cabersasi from Anyone.ai, Diego de las Casas from Mistral, Laura Montoya from Axel AI, and she is also from Latinx in AI, and Andrea Campos from Yana. They will discuss basically how to create a startup in Latin America. I think it's really important for us. And then research at academy and industry, Laura Alonso Alemani, from Universidad Nacional de Córdoba, Nando Di Freitas from Microsoft, Jeff Dean from Google Research, and Google DeepMind, Guillermo Sapiro from Apple, and Nayat Sanchez-Pai from INRIA, Chile. So, this is the program for tomorrow. Pretty busy as always. Questions there about the rooms? Anything? No? Great. And now coming back to today, these are the rooms for the practicals. We have diffusion models. You heard a lecture yesterday, and so today you have the practicals in room PC2 in economics, LLMs fine-tuning, PC1 in economics, and reinforcement learning, E10 in engineering. So those who are going to engineering, this is the map. So we are there. Well, you have been going, but maybe we are there at Faculty of Economics, and here's engineering, and this is the E10. And this is the metro station, just for reference. So there will be anyways someone taking, I think Paula or some volunteers will take you there, okay? We are done? Great. See you tomorrow. Maine, ¿te querés robar el agua hoy?